We are on. We can start even recording. Fine. Okay. So let me, on behalf of the organizing committee, let me welcome all the participants to this conference week of the GGI workshop. We had already a training week, and this is therefore the second week of the workshop, during which we will hear many talks every day. The aim will be not only to present more or less the state of the art in various aspects of the workshop program, but also, I think, to get the whole set of participants get to familiarize with each other, and therefore to prepare the ground to what we hope will be 3 weeks of workshop following this conference week. I think maybe I will say just a few words about how the conference week is organized. Well, today we have 3 talks. We decided to have a special day in honor of the recipients of the second Galileo medal. And the talks will be followed, each one will be followed by 10 minutes discussion. There will be a break after the second talk. In the next 4 days of the week, there will be 4 talks each day, also with some little breaks in the middle, and limited, I think, discussion time because, well, because the we had to cope with the different time zone and so on, so we cannot start very early and we cannot end too late. With this, I thank in advance the speakers of this week's conference. I thank all the participants, hoping to have, plenty of interactions this week and the following weeks. Now I pass the word to the director of the GGI, Professor Stefania De Curtis, who will introduce the speakers and will also chair today's lectures. Stefania?
Thank you, Gabriele. Thank you very much. It's a great pleasure to chair the first session of the workshop conference on gravitational scattering, spiral, and radiation. And as Gabriele said, it is dedicated to the 3 winners of the Galileo Galilei Medal Award of 2021. When the GGI became the National Center of Advanced Studies of the INFN, the Galileo Galilei Medal Award was established. And the medal is assigned every 2 years to 1 or more scientists who, in the 25 years before the date of the award, have achieved outstanding results in theoretical physics. And this is the peculiarity of the Galileo Galilei Medal Award, because it is not a career award, but it wants to favor young physicists and contemporary advances. The unanimous recommendation of the selection committee for this edition of the Galileo Medal was for 3 great scientists, Alessandra Buonanno, Thibault Damour, and Frans Pretorious, for advances in the analytic and numerical modeling of black hole mergers. So, waiting for the ceremony, which will take place next October 18 here in Florence, at the Villa Galileo, where Galileo Galilei spent the last years of his life, hopefully in presence, and we really hope to have all of you here in presence for this ceremony. We have the opportunity today to have them, all 3 of them, and I really thank the organizers to give us the opportunity to have these 3 review talks. The first one of these talks will be given by Alessandra Buonanno from Max Planck Institute, and the title is Status and Challenges of Theoretical and Experimental Gravitational Wave Physics. So I ask Alessandra to start this session. Thank you very much.
Okay. First of all, do you actually see my slides?
Yes.
Yes, maybe you have to make
see,
the screen. Okay, great. Very good.
Okay. Well, okay, so first of all, I would like to start by thanking Stefania De Curtis and the Galileo Galilei Institute. I feel truly honored and delighted to have been awarded the medal. And I hope I will be able to come to Florence in the fall. I also would like to thank the organizers for having me here today. Okay, so let me start. 5 years ago, LIGO published the first observation of a gravitational wave from a binary black hole that you see here on the left, the main plot from the discovery paper. And since then, 47 more binary black holes have been discovered by LIGO and Virgo, and 2 binary neutron stars. They are summarized, as many of you have already seen, I'm sure, in this plot on the right. This is the mass of the binary black holes in solar masses. These are the 2 black holes merging in a new black hole here. I will spend some time discussing some of what have been denoted as exceptional events, very high binary black hole, for example, this one. This other binary with a black hole component, and the other one we don't know yet, or we will never know. And there are 2 binary neutron stars here that you see merging likely in a black hole. So a few words about the last observing run of LIGO and Virgo that ended in the March of last year in 2020. This plot shows the so-called median of the range in binary neutron star in megaparsec as a function of time during the run. The range is basically the maximum distance at which a binary neutron star can be detected in the optimal configuration of Fezon with a signal-to-noise ratio of the network of 12. This also gives you an idea, again, of the distribution in the range with the median for the 3 detectors, and the increase of range with respect to the previous observing run, which was the second observing run. In terms of cumulative number of events, with respect to the first 2 observing run of LIGO and Virgo, which detected a total of 11 events, the first 6 months of the third observing run published 39 events, so the total is 50, as I was saying at the beginning. 23 public alerts were made available during the second part of the O3 run, and the analysis is still going on and will be published in the next months. Now, the interferometers have been under an upgrade, going through a new run in 1 year and a few months, not earlier than June 2022. It will be the 4th run. This is the noise spectral density of the detectors as a function of the frequency. And again, you see here the range binary neutron star. Is someone asking questions? No. Okay. And then after the 4th run, there will be a 5th run, 05, with even better sensitivity that will start sometime at the end of 2024, 2025. And at that point, one hopes to have CAGRA with a better sensitivity than today, and also the other LIGO interferometer in India at some point. Now, so we have been seeing several tens of events per year. We will go to hundreds of binary detections per year as we move to more sensitive runs. We will still be exploring what we generally call the local universe up to a redshift of 1. And this is the projection of the number of events, binary neutron star black hole, and binary black holes for the fourth run, as given in this living review relativity paper by the LIGO, Virgo, Kagra collaboration. The next decade is going to be also quite exciting with the new facilities on the ground, hopefully not yet funded, however, the Einstein telescope in Europe and the Cosmic Explorer in the US. This is underground and this is on the ground. And these interferometers are going to open even more the frequency band, as you can see in this plot here, going more toward the lower frequency, increasing the sensitivity by 1 or 2 orders of magnitude with respect to advanced LIGO, depending on the frequency band. And the improving sensitivity at lower frequency will allow actually to see black holes with larger masses, hundreds or thousands solar masses, up to large redshift, even redshift of 10. So the hopefully the what are generally called the seed black holes at the in very early time when the first stars formed. In the second part of the decade, we should have also a mission in space from the European Space Agency with a large contribution from the US, from NASA, that you see here, LISA. And this will open a new bandwidth at lower frequency in the millihertz. So black holes that cannot be seen on the ground because they are going to have too large masses. They are going to already merge in the millihertz. And these are binary black hole or supermassive black holes of million or billion solar masses that you can see in this plot here, just some of the possible signals that last for years in the detector. You see also the binary white dwarf in our galaxy. Some of them could be also, some binaries could be also observed individually, these stars here. Extreme mass ratio in spirals, these tracks that you see here. And also quite nicely, there will be stellar mass black holes of 30, 40, 50 solar masses that will be seen first in LISA, and then after several months or a year, they will merge in the detectors on the ground, hopefully the Einstein Telescope Cosmic Explorer. So for what concerns this talk, I will first, or this will be a bit intertwined, I will highlight the science that LIGO and Virgo have been doing from the latest observing run. What we have learned in particular for this handful of exceptional gravitational wave events, which kind of picture on the population properties of the black holes, the masses and spin is emerging. This is quite important because I want also to show what has been the role of the theoretical predictions for the two-body dynamics and gravitational radiation in interpreting these events, and also extracting the information. And we will also discuss what to do theoretically to keep up with the pace at which the gravitational wave detectors will be improving, as I was showing in the previous slides, in the next years and the next 2 decades. Okay, so let me start with the fact that we all know that gravitational waves carry information on the source, and the length, how much of the signal we measure depends on the bandwidth of the detector, and also on the mass of the object, and also the mass ratio. And in first approximation, you understand, yes? Sometimes I hear something. I don't know if someone is asking a question or I move on, okay? Okay, so from the Kepler law, you can determine actually the frequency given the separation of the binary system. And the gravitational wave frequency is just a multiple of the orbital frequency. And to understand which masses the detector are going to be observing, you can use the fact that the frequency, more or less at merger, is inversely proportional to the mass of the object with this number. And binary neutron star, which is a very long signal here, merge in the kilohertz. Very supermassive black holes are going to merge in the millihertz. Now, in order to extract information, theoretical models for the waveforms are used, and Bayesian analysis is used, but just to explain in a few just plots, from the way in which the frequency evolved in time, we can infer the masses of the objects. From the amplitude and the masses, we can infer the distance. From the time of arrival, the amplitude and the phase at the detectors, we can reconstruct the location in the sky. And if there are modulations, both in the amplitude and in the phase, we can actually know whether the binary was moving on a circular orbit or eccentric, and whether the spins were, precessing or just aligned with the orbital angular momentum, with the vector perpendicular to the instantaneous orbital plane. Moreover, by comparing two waveforms with deviation from general relativity, we can also probe the nature of gravity. So we need to solve the Einstein equation quite precisely. And in the last 15 years, this has been done by using the synergy of the two main methods. Analytically, one can solve the two-body problem in an approximate way. Plays a very important role post-Newtonian theory, which is particularly suitable for large separation, being an expansion in the velocity, the characteristic velocity, which is also intertwined with the strength because of the Weyer's theorem. Then we have, especially in the last couple of years, post-Minkowskian expansion of the Einstein equation, which is an expansion in G, which is not limited to low velocities, and in that sense is also more suitable for unbound motion and scattering, but can provide, of course, information also on post-Newtonian theory. It's included in the expansion. And one can do an expansion also in the mass ratio, so this is not limited to low velocities. This is particularly important when, of course, the two objects are at mass quite different from each other. We combine these approaches in one possibility in this effective one-body approach, where the different methods are incorporated, and then the full waveform, including the mergering down, is provided in an approximate way, and then is tuned and calibrated to numerical relativity. Of course, numerical relativity, and we will hear talks in this conference later on in the week, plays a very important role. And in this plot, I'm summarizing from one of the catalogs, but there are also others, the numerical relativity waveform, at least the point in the parameter space. This is the primary spin of the binary, and this is the mass ratio. For the different points corresponds to runs that include the precession of the spins or non-precessing the spins. And you can see a very good coverage up to a certain value of the spin. I remind you, the spin of a black hole, the maximum value is 1, and the mass ratio up to 4. But then there are gaps. And even where the waveforms are available, they are also quite short, let's say 20, 30 orbits or 40, 60 gravitational wave cycles, but we need to cover the entire bandwidth of the detector. It's very time consuming to produce these simulations. So now I will show you a couple of plots, a couple of slides about first what we do in the effective one-body approach, where we start from the post-Newtonian expansion. We resum this Hamiltonian in an effective Hamiltonian, which is a deformation of Schwarzschild or Kerr, and then the mapping produces a new Hamiltonian, which is written here. The main reason I wanted to show this is to say that these potentials that enter in the effective Hamiltonian are known up to a certain post-Newtonian order. That depends also on the symmetric mass ratio nu, as you can see here. In the nu equal to 0 limit, you recover the Schwarzschild potential, is just the first term. But then we add corrections that are not known today, and we calibrate them to numerical relativity. For example, this would be a 5 post-Newtonian correction. Then we solve the Hamilton equation with this Hamiltonian with a certain radiation reaction force. This actually study has been also extended to spins. So we have a deformation of Kerr. And then we need also to provide a model for the modes, for the polarization, the composing modes. And this is also done with a certain resummation of the modes, which I will not explain here in detail, but there is also a term that is tuned again to numerical relativity. So again, we have a waveform which is approximated up to merger, and including also the ring down, which is then tuned to numerical relativity. And this tuning is done, as I said, mainly by adding these higher order post-Newtonian corrections in the potential that enter in the effective Hamiltonian, but also in the waveform itself. And here is a plot that shows if you don't do anything, if you don't include corrections, calibration to numerical relativity, the two waveform, numerical relativity and AOB, will be accumulating a certain difference as you go toward merger, but then you tune the model until they agree very well with numerical relativity. Over the years, this calibration has used also waveform for the merging down produced in the test body limit, solving the so-called Wheeler-Zerilli or Tchaikovsky equation. This is an example of the waveform for a spin close to maximal 0.99, just for the Tutu mode. You see the shape. And now the way in which all this is used is that one produces numerical relativity waveform for some parameters. This is a combination of the spin of the two objects. This is the symmetric mass ratio. These waveforms are produced solving the Tchaikovsky code, as I said, for very large or small, actually new test body limit. Other waveforms are produced with numerical relativity. They are used to tune the model. Some of them, after we expand the model everywhere in the parameter space, they are used to validate the model, which is an interpolation, and in some region, even an extrapolation. So we need to make sure that at least in the region in which we can produce numerical waveform, the extrapolation agrees with, at a certain level, with the numerical relativity results. Now, there are two other methods that also are used in the LIGO and Virgo collaboration to produce waveform models. One here on the left, it's a phenomenological model, which is quite effective, being very fast because it's produced in closed form in frequency domain, and is used by, first of all, we say hybridizing, merging together, matching in time domain an effective one-body model with a numerical relativity waveform in the last part, and then fitting the whole expression, a closed form expression in frequency domain, introducing some parameters. IMR phenomena, remember this acronym for some plots later. And in frequency domain, the amplitude, the gravitational waveform can be written as an amplitude and the phase, e to I phi, the phase. And these parameters, lambdas, are tuned, are the parameters that are added to tune against this EOB numerical relativity waveform. And the fact that one can write the signal in this closed form in frequency domain relies on the fact that if you were plotting the amplitude and, for example, the derivative of the phase as a function of frequency during the spiral, intermediate, and merger region, ring down region, they are quite smooth functions. So it's not very difficult to add parameters, although there are many parameters, and produce this model in frequency domain in closed form. The other approach or model that also can be used are the so-called numerical relativity surrogate models, where one directly interpolates the numerical relativity simulations. However, these models, although are very highly accurate, they are in the region in which they are available, they are most accurate because they are just interpolating the numerical relativity results. They are limited in the region in which we have numerical relativity waveforms, and also in the length, because we know numerical relativity waveform only, up to a certain range on average. I'm sure people in this conference will show you also some very long waveform, although they are not, available in a very large part of the parameter space. You can make this enhanced surrogate much longer if you hybridize again with the EOBNR waveforms. And this is just a plot that shows some, agreement between these numerical relativity surrogates and the EOBNR and the numerical relativity itself. Okay, so now I want to, before I start also showing you some results from the data of the third observing run, I want to say what are actually the waveform models that have been used for the analysis of the the first 6 months of the third observing run of LIGO for binary black holes. So this IMR phenomenon, the enhanced surrogate, and the effective one-body numerical relativity waveforms included for the first time higher harmonics and also precession of the spin for quasi-circular orbit. I'm going to discuss mainly, except one slide.
You could say
yes?
Alessandra, me too. I'm actually, all the participants are muted, so I don't know this noise.
But
go on, because I really don't know. We are checking, okay?
Okay, no, don't worry. It's okay.
I'm sorry for that.
No, it's okay. So here in this formula, you have the polarizations, decomposing modes, and with -2 spherical harmonics. And this angle is the angle that the observer forms with the direction perpendicular to the orbital plane. Now, the dominant mode is the tutu mode, the quadruple mode, we call it in general. This plot is supposed to show you the importance of the higher modes as a function of the mass ratio at merger, at the peak, relative to the dominant mode. And the bottom line is that if you increase the mass ratio, for example, 10, the 3-3 mode and the 2-1 mode, they can become 25%, 35% of the dominant mode, of the tutu mode, which is saying that you have to include them if you have a system, with large mass ratio of that kind. Precession is also important in higher harmonics, and this plot is just showing you an example that if you have a numerical relativity waveform in gray with higher harmonics and precession, and you take a model with only precession but not higher harmonics, you see some differences. We generally measure this, the goodness of the model against the NR data with a quantity that we call unfaithfulness. If it is very close to 0, it's good. So here we have this number. If you include the higher harmonics, you can improve by 1 order of magnitude. And here you don't see much difference with the gray and the blue. The binary black hole waveforms depend in total on 15 parameters. So we have the two masses, the spins, each of them is a vector, but then we have other parameters, the distance to the source, the angles that the binary form with a detector and a polarization angle, etc. With the neutron stars, we add one new parameter, the Tyler deformability, that we will see later. So we have 1 or 2 more parameters depending on a binary neutron star or neutron star black hole. Okay, so now in order to appreciate the theoretical work, let's look at some of the events, and in particular, I start with the exceptional events. 1908-14, this has been classified as a binary with a puzzling companion. Why? The primary mass is very clearly a black hole because it had a mass larger or the order of 23 solar masses. By the way, I care here to put an error because it gives you an idea of how well we can measure these masses with the models we have today. The secondary mass, it's a bit peculiar because it's around 2.6, with an error also, which is quite interesting because it's small. We generally say a neutron star has a mass maybe 2.1, 2.2, based on binary pulsars actually. Could be a little bit larger, but here is not clear whether it's a very large neutron star or a very small black hole. And in this event, you can already see the mass ratio is 10. I was just telling you that if you have a mass ratio 10, you have to care about higher harmonics. And here I have a simulation that shows this system. It's not a numerical relativity simulation because it will be too long to generate. It's actually produced with a EOBNR waveform. And you can see here the fact that around 9 seconds before merger, here you see the L equal 2, M equal 2 radiation, the L equal 3, M equal 3 radiation. You have to go at 4 seconds before merger to start see if you can see that. The L equal 4, M equal 4. And then very close to merger, just a couple of seconds, 1 second, you see the blue, which is the L equal 5, M equal 5. So the more asymmetry there is in the binary, the larger mass ratio, the more asymmetry between the spin of the two objects, the more you can see of these higher modes. Now, to be more quantitative, I want to show here the plot of the masses of the two objects reconstructed with a Bayesian analysis. After you marginalize on the other parameters, you get the one-dimensional posterior distributions. And here now the acronyms, this EOBNR, precession higher modes, IMR phenomenological model precession higher modes. You don't see much difference between them. And the 90% are here, credible regions. So systematics are not a problem for these sorts. On the right, this is what was very crucial to interpret this signal to get the mass of the secondary quite well. And you can see that if you were not adding, for example, precession, the posterior distribution will be wider. And on the other hand, you can get constraint more tightly, posteriors if you add precession, both for the, the two models, EOBNR and phenom. Now comes another exceptional event, which was 1904-12. This had a mass ratio between 3 and 4, so Q was 0.3. You see here, this is a numerical relativity simulation, and you see, you will see later more this little spin of the black hole, of the primary black hole. In fact, the spin for this binary was measured at the level of 0.4, 40% with respect to the maximum value. And the inclination, the tilt angle of the spin was around 45 degrees. And now for this system, for which we start seeing also some spin effects, non-negligible, you can see there is more difference between the two models, EOBNR and phenom. And this is the posterior distribution for the combination of the spins of the two objects, of the two component black hole and the mass ratio. And I have also another plot here that shows, again, the mass ratio, which was important because this was really the first binary black hole which had some asymmetry. And you can see the posterior distribution being, there is some difference here. But still, if you look at the 90%, which are represented by these lines here for each model, they are still, overlapping with each other. So we are still dominated by the statistical error, not by the systematics due to the modeling. Now, the last exceptional event I wanted to discuss is the 1905-21. This created more challenges because it was a very short event because of the high masses, around 90 for the primary and 67 for the secondary. In fact, this black hole, in particular the primary, had a mass that today cannot be explained by collapse of massive stars because of pair instability supernovae. But because the signal was very short, it was very difficult to interpret, although we had results with quasi-circular orbit, models represented here for the two masses. Again, the combination of the spins perpendicular to the orbital plane and on the orbital plane. But for this event, we had the largest difference between the models, even including, higher harmonics and precession, although the 90% credible regions are still overlapping. So we are not dominated by systematics. Okay, so now let me actually tell you something more. If you put together the different events of the entire catalog, which I said are 50, binary systems that have been discovered by LIGO and Virgo. So what we learn from that? So this is a plot that represents the mass ratio, and here you see the total mass, and many events, the two-dimensional posterior distribution are represented here. The color represents the exceptional event, together with some other events which were also quite peculiar. For example, this one was perhaps neutron star black holes because the mass of the secondary was, small, but was also clear because the signal to noise ratio was not very large. This object here was the least massive system composed of two black holes, so a binary with the smaller masses. I have another plot here that shows the spin, again, chi effective and the shear mass. So we had the objects with the largest chi effective or the smallest chi effective. So we start seeing, as I said, a certain variety. There are no longer these vanilla events like the one observed with the first and second catalog. I have another plot here that shows all the events, the posterior distribution for the two masses, the mass ratio, chi effective, and the distance. Okay, there are some, comments to make about some of the events having the mass of the binary black holes, of the black holes in this mass range. 3 binaries for which one of the mass was larger than 45 solar masses. Quite interestingly, there are events for which we can really conclude that the spin was larger than 0, that the black holes were non-spinning at 95% of credibility. Finally, about the precession of the spins, this parameter chi-p, so I have a plot here. These are the posterior distribution compared with the prior distribution for chi-p. And the only thing I want to say is that the two exceptional events I was describing before, 1904-12 and 1905-21, are the events for which we can conclude that there was a mild sign of precession. The others, more or less, we cannot say much about precession. Okay, so now let me go back to the modeling. I have still 13 minutes in my, I don't see anything, so please at some point tell me that I have to stop, but in my time here I have 13 minutes. Okay, so on the left, I want now to go back to the accuracy of the waveforms that have been used to extract information from all this data of LIGO and Virgo. So this is a study in which the two waveforms I was mentioning, which now I'm calling with these technical names, have been compared with numerical relativity waveform from the SXX catalog 1344. Notice that these waveforms were not calibrated in the processing sector with numerical relativity. We will do that in the future. And these two plots show the so-called unfaithfulness, what I was describing before, which if it is very small, it is good. Now, very small for us means, let's say if it is less than 1%, it's okay, but we start worrying when it is larger than 1%, which is 10 to the minus 2. And in some cases, you see, in particular for IMR phenom, it can go even above 10%. Now, numerical relativity waveform, are not available everywhere. Although, 1,300 is a large number, but we don't know them everywhere in the parameter space. So besides comparing with numerical relativity and noticing that there are some, differences, we also compare with each other. So if we have two models that we can, evaluate everywhere in the parameter space, even where there is no numerical relativity, we can compare with each other. This gives us an idea of what are the regions where we need to improve these models. And this was done in this plot here. Again, the unfaithfulness colored, where is light means bad because it becomes larger than 1% up to 10%. And again, between these two models, IOBNR and IMR phenomenon. And what you can see is that the unfaithfulness, when the mass ratio is, for example, 20, and the spins are larger than 0.6, well, it can be larger than 10%, okay? Now, maybe for you, what is, you might not appreciate what is 10%. I mean, which kind of differences in the parameters we can have when we have an unfaithfulness of 10%. Okay, so you can do a study. You can basically take the noise spectral density of the next run of LIGO of 4, and you can do a synthetic injection of a signal. So you inject the signal synthetic from numerical relativity in the data. And you take, for example, a binary with this mass ratio, this combination of the spins, and you put yourself in the most problematic situation in which you are looking at the binary edge on, which is the case which amplify the presence of the higher modes. And so, and then you do a Bayesian analysis. You try to extract the parameters, and you ask the question how well you can recover these parameters. So I show you the result. So in this particular case, this numerical relativity waveform had a difference with the models of 4% for SOBNR and 9% more or less with IMR phenomenon, with a signal to noise ratio of 20. And this is the recovery of the two masses. This is the injected value, which is within the 90% for IOBNR, but it's close to the border here. But it's actually close to the border completely from the IMR phenomenon, which is around 9%. If you look at other parameters, for example, the spin of the primary or the tilt angle of the spin with respect to the orbital angular momentum, a 9% of unfaithfulness will give you a positive distribution which doesn't encompass at all the injection value. And this is something you don't want because you will basically misinterpret. You will not get the right value of the spin or even the tilt angle of the object. So we need to improve that. So let me now, I've described the case of binary black holes. I want now to switch to binary neutron stars and then come back to the modeling in a more global way. So for binary neutron star, as I said, there is a new parameter that we are very much interested in measuring, which is the tidal deformability parameter. This is due to the fact that the neutron star is deformed toward the end, and the waveform will be different from a waveform with the same parameter, the same masses and spin, but the one produced by a black hole. And you see here a cartoonish kind of plot that shows the difference as you go toward merger. So we want to determine this tidal deformability parameter that will give us information about the equational state of neutron star. So what neutron stars are made of in the core, in the inner core. And this is something which is available with the neutron star coalescence and not with other, experiments that are also are happening also on the Earth, which are probing the so-called conjecture state of matter, matter at very high density and pressure. Okay, so the work of producing inspiral and actually merger, not much, but let's say inspiral waveform for binary neutron star has also been done at the interface between analytic and numerical relativity. And I want just to show you now one example from the binary neutron star that was observed during the third observing run. You are very familiar with the first one because that was, that started multi-messenger astronomy. But I want to show you the 1904-25, which was also an interesting binary neutron star, the only second binary neutron star observed. And these are the posterior distribution for the masses, for certain choice of the priors for the spin of the neutron star, 0.9 and 0.05. You can see different depending on the spin. This is the mass ratio. This is the symmetric spin. It's the symmetric spin. Again, the combination of the spin perpendicular to the orbital plane. The peculiarity of this binary neutron star was actually in the total mass, because the total mass was quite different from what actually has been observed as total mass from binary pulsars in our galaxy. And here you can see, in fact, the distribution of the one in the galaxy observed in electromagnetic spectrum, and this is actually the posterior distribution for 1904-25. About the tidal deformability parameter, I should say that it was not measured constrained as well as 1708-17, and this is the posterior distribution for lambda. The constraint was much tighter for 1708-17, where you see that it's much broader for this new binary neutron star. And the main reason is basically the signal-to-noise ratio, which is around 13 instead of 34 for 1708-17. Now, what are the prospects of this for the future? How much we have to improve the waveform for binary neutron star? Well, if we were detecting in 04 a binary neutron star like 1708-17, 40 megaparsec, the signal-to-noise ratio would be much larger. And also here, you can do the kind of injection study that I mentioned before. And you can take one of the models with tidal effects. You can inject in the data and you can see how the other models can recover the signal. And this is taken by a paper by Samajar and Dietrich. This model, it's not important, the name, was injected in this analysis for the O4 run, O4 sensitivity. And the injected value for lambda tilde is here. And you can see if you use other waveform model like post-Newtonian theory or EOBNR, you cannot encompass the injected value. And in fact, other studies also have been done, also for third generation detector recently, this one. And the conclusion is that if you want, even for the next runs, as this plot shows, but in particular for third generation detectors, if you want to get the radius of the neutron star with a precision of 1 kilometer or less, we certainly need more accurate waveforms. Okay, let me skip these neutron star black holes. I want to say that the next important step is really to include the precession in these waveform models. And this is very important in order to distinguish the different formation scenarios for binary black holes and also binary neutron stars. And the only thing I want to say is that in particular in the last 6 months, there have been many papers because everybody is preparing for the next round of 4. At the moment, although there has been a lot of progress, we still don't have eccentricity with higher harmonics and precession, but we have very encouraging results already with higher harmonics and the eccentricity and spins align with the orbital angular momentum. So I'm quite confident that some models will be available in a 1 year time scale when O4 will become important. Now, I will skip these slides on testing GR. Let me go to, in the last few minutes, I want to go back to the modeling. So this is particularly important for this conference, I would say. In the last 2 years, there have been, several groups that are applying these new tools that come from scattering amplitude and effective field theory to the two-body problem in general relativity. And recently, the local in time two-body Hamiltonian at 4 post-Minkowskian order has been obtained. This corresponds to 3 loops. And I'm showing here only the results at leading order in an expansion in G. So once you have the amplitude, a Fourier transform will allow you to compute the potential. And this potential now has been computed up to, as I said, 3 loops, although only the local in time part. And this is why in this plot here, this 4 p.m., I'm using these dashed lines here. So just to start to understand the impact of these results for the modeling, I'm showing you now some comparison that we did recently, although this is not conclusive, with, for example, the binding energy computed in numerical relativity, which is one of the building blocks to compute the waveform models that I was describing before. So I have a plot here that shows the binding energy for circular orbit as a function of the frequency from 40 gravitational wave cycles up to 2 cycles. So until the end, I need just a couple of minutes, to finish. And here you see the 1 p.m. Hamiltonian result from 1 p.m. The 2 p.m. in Zion, the green is the 3 p.m. Better agreement, up to 10 gravitational wave cycles before merger. And this is an example of the 4 p.m. result in orange. Now, as experts here know quite well, this is in the local in time, means there is a piece that is proportional to 1 over epsilon. So we drop that piece and then put epsilon to 0 in the rest of the expression. This piece will be cancelled by the non-local in time part, but that part will also introduce a finite term, which we don't know at the moment. So keep that in mind. This is not conclusive. We also introduced this result in the effective one-body formalism, and so now these are the Hamiltonian in the UOB formalism, also for this local partial result, which agrees quite well with the 4 p.m. Hamiltonian non-calibrated to numerical relativity, which is the starting point of the UOB-NR model that I was explaining to you before, that is used in the LIGO-Virgo data. So this is all very encouraging, but just to say more work is needed in the future. One slide before the end. So I want also to say that this work, the interplay between all these new techniques and methods, have already produced some interesting results. For example, spin orbit Hamiltonian computed last year at 4.5 post-Newtonian order. And here you see the plot from the paper, the binding energy, the comparison with numerical relativity in Zion for a mass ratio of 1 and 3. This is the next leading order spin orbit Hamiltonian computed. You see the improvement in accuracy with respect to numerical relativity. The Hamiltonian has been computed partially at 5 p.m. and 6 p.m., also using these methods in this paper. There has been results at 2 post-Minkowskian, 1 loop for spinning and precisely in black holes, both spin orbit and recently also spin-spin, tidal effects in post-Minkowskian expansion, and finally, just in the last few months, leading order radiation in the post-Minkowskian expansion. All this very interesting. So let me now conclude. So as I try to motivate the observing gravitational waves is very much relying on this precise prediction of the two-body dynamics and gravitational radiation. With the first 2 runs of LIGO and Virgo, we have observed the tip of the iceberg of the binary population, but already with the third observing run, a much richer picture of the population of black holes is emerging, and I gave you some highlights with the inference of properties from the exceptional sources that we have seen until now. So it's crucial to improve the waveform models already for the upcoming runs, already for 04 and then 05, and then for the future detectors. Now, if you think about the signal to noise ratio that we will be observing, today is more of the order of 10. We are going to see 100 and even 1000. Already by that, we need 1 or 2 order of magnitude of improvement of the models that we have today, including numerical relativity, by the way. So I want also to say that, effective field theory scattering amplitude have brought a new fresh perspective and tools, unveiling also new paths to intertwine these different perturbative approaches, PM, Minkowskian, and gravitational cell force. The impact of this result has not been fully assessed. We need more work, and I think this will come in the next year, because as we prepare for the new models for the upcoming 04 run, so there is unique opportunity for theoretical particle physicists to contribute. I put back this table that we used, for some of you remember, in the workshop last August of rethinking the relativistic two-body problem in general relativity here at the Max Planck Institute. And well, some progress happened in the last 8 months, but we still need, I believe, to go really to 6PM. We want to approach it with post-Minkowskian calculation. This would mean 6 loops, I'm afraid. I think the goal is really to produce in the next years, it will take some time, the dynamics, the radiation, including the waveform for spinning objects. I think really 6PM is needed. And you don't need to do everything analytically. Some of these results can be obtained also numerically. Thank you. Sorry for taking, I think, 3-4 minutes more.
Yes, 3 minutes is not a problem. Thank you, Alessandra.
At least I left some time for questions.
Thank you very much for this clear and exhaustive review, and to show how the complementarity of analytical and numerical calculation played a crucial role in your research. And also how your research proved to be of great importance for the analysis of the experimental data. Thank you very much. And now it's time for questions. I think all of you are muted, so please raise your hand if you have questions, and I'll try to unmute you. You were too clear.
There is something in the chat. I don't know whether
something in the chat. No, but actually it's just my request to raise
a lot of information.
No, your slides are wonderful, really. Now I'm very happy that the time for having new results and new progress is not so long, like the collider physics timeline. We hope to have new data and also new very, very big progress in analytical and numerical calculation very soon, and this is exciting. There's one question. Let me try. Gabriele, ask to unmute. Gabriele, you can unmute yourself.
Thank you.
Okay, great. It worked.
Thank you, Alessandra. It was a beautiful talk. Of course, you concentrated on gravitational wave detection from the binary system, which is the theme of this workshop. So this is excellent. On the other hand, perhaps if you have some, if there are no questions about that part, I was wondering about other applications of gravitational wave detection, like stochastic backgrounds, whatever you can think about. Other use of gravitational wave detections.
Yeah, so certainly for, okay, so for...
And what are the perspectives?
The current ground-based detectors, the stochastic background of gravitational waves, for example, produced by the binary black holes and the binary neutron star that we are seeing, is a target. And you know, what I'm saying is that we are seeing all these binary black holes. Okay, so one can compute a stochastic gravitational wave background out of the population. And in fact, the estimate is that for the next run and more actually 05, there are good perspective to see, depending, there is an uncertainty in this background, to see actually this background. So this is an astrophysical background due to binary black holes and also actually binary neutron stars. Now, you might, maybe you were thinking more on the cosmological background from the early universe. Well, the LIGO and Vigo collaboration just had recently in the last months a new paper with you know, the new bound. I think, if I remember correctly, now I don't have a slide, but the omega gravitational wave is at the level of 10 to the minus 9, if I remember correctly. Actually, some here might maybe remember more the exact number. But anyway, yes, the stochastic background is also another search that is done. There are searches also of, you know, continuous waves of neutron stars that are rotating, and they have some bumps on the surface, very small bumps of the order of centimeters, that can produce gravitational waves. But that all depends on the so-called you know, ellipticity of the neutron star. And we don't know if the values of the ellipticity will be large enough to see this kind of signals in 04 or 05. So this will be more for the next generation of detectors, like the Cosmic Explorer or Einstein telescope. So continuous waves, you know, stochastic background, binary system, supernovae, of course, but the supernovae, we have to wait also for Cosmic Explorer and Einstein telescope, because the rate at which a supernova will happen in our galaxy or close by galaxy is it's not very high to see them with the current detectors or the next, you know, few runs.
Thank you.
Thank you very much. I don't see other hands raised, so I just thank Alessandra for the nice review. Maybe we have a question also at the end of the session. I don't know. And let me now ask Frans Pretorious to show.
Okay, hi. So can you hear me now?
Yes. Hi. How are you?
I'm good, thanks.
Okay. Nice to meet you. So you have 35 minutes and then question for explaining the progress and challenges in numerical relativity. Thank you.
Okay, thank you. So let me try to get my screen share going. Sorry, give me a second.
Oh, great. No
actually, yes, I'm trying to find the option. So do you have to allow screen sharing for me to be
I think you are allowed because you are co-host. So.
Okay, so let me my slide. So can you see my screen, or
No,
are you still just seeing me?
Not yet.
Okay. So apologies, I'm trying to get this.
There should be a share screen.
Yes, a share screen button.
A green button on my.
Okay, great. Now I've got it. Yeah, sorry. I'm usually the host, and so I have to allow others to share. So,
you can do it numerically.
Okay. Yeah. Okay. So can people see?
Okay, great.
Okay, great.
We see it. Try to do it. Great. Very good.
Working?
Please.
Okay, great. Okay, well, again, I want to start, as Alessandra did, by thanking the committee for the award. It's a great honor to have received it, and together with Alessandra and Thibault. I'd also like to thank the organizers of the conference for inviting me to speak. It's a great pleasure, and I hope I can give an interesting talk. Okay, so what I'm going to talk about is progress and challenges in numerical relativity. And this is sort of a brief outline of the talk. So I'll first start by just describing how numerical relativity fits into general relativity. And then I will sort of broadly outline what, in my opinion, are the three main challenges going ahead in attempting to solve various problems of interest. And these are the challenges of well-posedness of the equations, the gauge or the coordinates that you need to represent a particular space-time, and the computational expense of the problem. Now, I could probably have spent the whole 45 minutes just listing various examples where progress has been made and where challenges remain, but I thought it'd be more interesting to go into a little bit more depth in a couple of examples. And so the two examples that I've chosen to illustrate, one is dissipative relativistic hydrodynamics. And you might say, okay, well, that's not quite gravity or general relativity, but of course, that could be very important in mergers of neutron stars. And the reason why I chose that is to illustrate this issue of well-posedness. I think it's nice to have an example of a theory where at least we're very sure that viscous effects should be present to some degree. So that's why I chose that example. And then on the more sort of a completely theoretical side is the question of understanding what is the interior structure formed inside of black holes formed from gravitational collapse. Okay, so numerical relativity, I want to emphasize it's not a subfield of research in general relativity. So it's a bit of a pet peeve of mine that I'm called a numerical relativist, where I'm labeled by the tool that I use. That's kind of unusual in science. I just want to say, so I'm not a numerical relativist, I'm a relativist, and I just happen to use numerical tools more often than not. So that's all that numerical relativity is. It's applying numerical methods, and in particular, methods geared to solving the partial differential equations of classical general relativity. And it's most useful in regimes where other methods, complementary methods, might not work that well. And in particular, these tend to be situations where the nonlinearities of the field equations are sort of most strongly manifest in solutions. So there are advantages and disadvantages of using numerical methods, and we just list a few. So I think that the pros of numerical solutions are that once you have an algorithm that can deal with a certain class of equation, the complexity of the equation doesn't matter. How much detail you have to put in initial conditions don't matter up to a point. And how nonlinear they are, at least as if your algorithm works for that, that doesn't matter. So once it works, these things aren't an issue at all. Another advantage, or arguably an advantage, and this is relating to one of the themes that I'm going to be mentioning is the well-posedness, ill-posedness of equations. That if you try to solve an equation which is mathematically ill-posed on a computer, it will fail, it will crash, you won't be able to do it. So it's very unforgiving to ill-posed problems. And why that's perhaps relevant in certain situations is in many cases, in particular modified gravity theories, exotic compact objects, people propose interesting theories, but the underlying equations are ill-posed. And sometimes pencil and paper, you can get some solutions, but then the question is, what is the meaning of those solutions if fundamentally the equations are ill-posed? Well, numerics doesn't even give you that choice. If you try to solve an ill-posed equation, you'll fail. Then another thing which I like about numerics is that you get to look at full solutions. In fact, you have to look at the solutions. So, unless you want to look at streams of numbers and data, which is not very intuitive at all, you have to visualize your solutions. When you solve a problem numerically, you get the full solution. You can look at every aspect of it. Now, some of the cons. Well, one thing, especially with situations related to complicated equations like the Einstein equations, is that it's often a very time-consuming effort to develop a code for a particular situation, and it's not very easy to adapt that to a new problem. So you often have to, it's a several months to a few year effort to even longer to build a stable code for a particular situation. And you need to build a new one essentially for every new problem that you're interested in. So on a related front, there are no back of the envelope shortcuts that you can make sort of to get a rough insight in the beginning. If you wanted to do that, you'd have to write a separate code that does that back of the envelope type shortcut. So either you solve the full problem or you don't. So you kind of have to deal with this effort to get even sort of the leading order answers. Now, this third point, you might think I perhaps forgot to delete the line from the previous slide, but that this is actually also a con, from a certain perspective, that it's unforgiving to ill-posed problems. Because sometimes you might have, some theory, you don't quite have the equations in the form that's, amenable to a classical, partial differential equation solution. But perhaps, by pencil and paper, you can still tease out some interesting properties. Well, if that's the case, you can't use numerical methods because it's unforgiving to ill-posed problems. So that can be a con or a pro, depending on how you look at it. And of course, the converse of, on the previous slide, of being able to look at full solutions and explore every aspect of it. The downside is you can't sort of get parameterized families of solutions easily. You essentially look at one solution at the time, and trends amongst families of solutions you have to then, after the fact, tease out. Okay, so what are some of the remaining challenges related to gravitational problems? And here I'm sort of speaking kind of in a very broad sense. I'm going to focus on three, and I put in a fourth here just for an historical context. So I'd say the three main challenges are: one is there are no fundamental issues, it's just expensive. We just don't have the computational resources to solve a particular problem. The second one, and this is particular to nonlinear theories like general relativity, in a dynamical sort of strong field setting, it's often unclear what the coordinate conditions, which I'm calling the gauge here, what coordinate conditions are needed to reveal the full solution of interest. And in particular, in some of these dynamical settings, it's even unclear how you differentiate between, quote, gauge and true gravitational wave degrees of freedom. And why this is sort of particularly sort of problematic, it's unlike when you take a textbook example of a solution to general relativity, you apply coordinate transformations to view it in different ways. Certain coordinates are better in describing certain aspects of the problem. When you're solving for a space-time numerically, you don't know what the space-time is, and you don't actually know what the coordinates are as you solving it. So in some sense, you're simultaneously solving for the space-time and the coordinate system as you're going ahead. And so choosing a dynamical gauge that reveals the full space-time can be a significant challenge. And the third one, and this is mostly, again, for sort of beyond general relativity theories or modifications, in particular as applied to gravitational wave astrophysics these days. There's a lot of interest in trying to use the measurements of LIGO to test general relativity. And one way of doing that is to explore the consequences of alternative theories. And one issue with a lot of these theories is that the corresponding classical equations that we can solve numerically, it's unclear whether they're well posed in a mathematical sense. And some of them are, at worst, they're just blatantly ill posed. So that's a particular challenge of dealing with sort of some modified gravity theories. And this fourth point that I mentioned here, I think just for a historical perspective, that if I'd given this talk 20 years ago, and this is sort of when I entered the field, one of the major problems to get the two-body problem working was, even if all these other problems are dealt with, and in general, vacuum classical general relativity, they are dealt with now, there's still the issue of during a free evolution, a so-called Cauchy evolution. One feature of the Einstein equations is that they have constraints, the Hamiltonian momentum constraint. And it was quite a challenge how to keep those constraints under control during a numerical evolution. But today, I think that's essentially a solved problem. Okay, so now I'm going to sort of very briefly just list a few sort of areas in which there are still open challenges before looking at those, a couple of specific examples. And in some sense, the converse, the things that the regimes of parameter space that I don't mention here, I think significant progress has been made. And Alessandra showed lots of very nice example movies from, especially binary black hole regimes where significant progress has been made. So for binary compact object simulation, so black holes or neutron stars, I think where there's still challenges that have to be overcome is in so-called extreme limits of parameter space. So for astrophysically relevant mergers, that includes large mass ratios, so 10 to 1 or higher, higher centricities, if long inspirals are needed, and in neutron star mergers, if long post-merger evolution is needed for long-lived remnants. And here I think the issue is largely that of computational expense. It gets very expensive to do things. There's no fundamental issue that needs to be resolved before those situations can be studied. On a theoretical side, a problem that I'm often been quite interested in is sort of the ultra-relativistic limit of black hole collisions. So what happens when you smash two black holes together at close to the speed of light? I'm not going to say anything more about that. I think just the many interesting aspects to that problem. And there's a combination of having a good gauge to solve the problem and computational expense. Now, another case where for black holes that's very interesting, where we still don't have a lot of answers, is black holes that are nearly extremal, Kerr black holes that are nearly extremal. So they're close to A = 1 in the spin parameter. And this could either be in a single situation, for a single black hole, if you're trying to look at perturbations of this black hole, or modeling such high spin black holes in binaries. I'd say today, perhaps, it's reasonable. There are some simulations, going up to 0.99, perhaps even one more. And for those spins, it's mostly an issue of expense. On the other hand, for some of the more interesting theoretical questions, and I put theoretical there with a question mark, because I'm not sure how rapidly black holes spin in the universe, but at least theoretically, there's suggestion that there's some interesting physics that go on in the near extremal or extremal limit. For example, there's been a suggestion that the quasi-normal ring down of black holes becomes turbulent if you go sufficiently close to extremal. But the estimates there are you need perhaps 4 or 5 nines in the 0.999 to actually see those effects. And at that point, there are also issues of gauge. Like, how do you actually, when you include back reaction, how do you design a code that can actually explore that? Another area where there's still a lot of work to be done, that's in when modeling neutron stars. And a lot of that is just related to expense. I'm not even worrying here about things about the matter physics that we don't understand, like the equation of state, but just matter that we expect to be there. For example, magnetic fields. And there's one example that I listed there, is that when a merger happens, there's a lot of dynamics that happens on spatial and temporal scales that are just too small or just too long or too large to be able to resolve. And so that's an issue of expense. One example where it's about well-posedness, that is if we need to include dissipative effects, so viscosities or heat conduction. And there's a sort of a long-standing issue about whether the theory that we have to do that, the relativistic Navier-Stokes equations, is well-posed. And so I'm going to use this as an example of this well-posedness issue. As I mentioned before, there are many other examples, in modified gravity theories or exotic alternatives to black holes. But I thought sometimes it's a little bit too easy to pick on some of those examples. So I'll restrict us to relativistic hydrodynamics, which is actually a very sensible theory in all respects. And as I'll show, as it's only recently been, I think, really understood that it's actually that our theoretical models of it actually are completely sensible. There really is not a problem if you do things properly. Now, when it comes to sort of some more theoretical questions in classical general relativity, I think most of the open problems are related to gravitational collapse in some manner, whether it's the nature of singularities, cosmic censorship, etc. So it's in sort of the strong field dynamical regime where black holes have formed or they're about to form. Just to give a couple of examples, so in the critical phenomena discovered by Matt Choptwick almost 30 years ago now, that's been very well studied in spherical symmetry, but there's comparatively speaking, very little work outside of spherical symmetry. And I think that's largely an issue of gauge. We don't really we don't really have good ideas about how to fully uncover the dynamics that happens when you go away from spherical symmetry. Similarly, to understand the nature of the interior of black holes, there's been a lot of work in spherical symmetry. So I'd almost say it's a solved problem in spherical symmetry. By going beyond spherical symmetry, again, there's similar problems. And this is one example that I will illustrate. The second example, so what's the issue of the coordinates or the gauge in this case. And also just very briefly mention that the analogous problem of singularities in compact spacetimes, the so-called the Big Bang singularity, that's actually a lot less challenging from a gauge perspective. And so we can actually go a bit beyond that, but then we find very interesting things that form these so-called spikes, and then it becomes an expense issue. So briefly give an example of that. Okay. Okay, so let me now talk about relativistic hydrodynamics, and this is an example of this challenge of well-posedness. So hydrodynamics sort of governs the behavior of macroscopic distributions of matter that are in or near local thermodynamic equilibrium. So we know matter is fundamentally microscopic and quantum, but in situations where we can describe sort of average properties of matter by so-called hydrodynamic variables like energy density, fall velocities, pressures, etc., then there are sort of a set of conservation laws that govern the dynamics of these large-scale distributions of matter. That's what we call hydrodynamics. So the conservation laws, they're essentially in 4 space-time dimensions. There are four equations that you get from conservation of the stress energy tensor, and 1 additional equation for each so-called charge that you have in the problem. So for example, one you can consider as a charge, for example, if you model fermions is the baryon number, have a conservation law for the baryon number. So very simple ideas, very simple equations, at least in principle. And then, of course, typically there are many, many more variables of interest than there are conservation laws. And to get a closed system of equations, you get that from the so-called equation of state, which defines the necessary relationships between all the rest of the variables so that you have a closed system. And one of the simplest examples of one of these relationships is the pressure as a function of energy density. So the simplest hydrodynamic theory, if you will, is so-called ideal hydrodynamics, or a perfect fluid. These are given by the Euler equations, just known for centuries. And they're sort of trivially upgraded to a relativistic version. So if we write the stress tensor for an ideal fluid, instead of using three vectors, we use four vectors. And in the conservation laws, instead of using ordinary derivatives, we use a covariant derivative. Then we get a perfectly well-posed, sensible relativistic theory of ideal hydrodynamics. And I just mentioned, technically, it's only well-posed in a weak sense, because in ideal hydrodynamics, generically, shock waves are represented as discontinuity, step function discontinuity. So you have to sort of deal with these equations in a weak sense in ideal hydrodynamics. And essentially, for the bulk of neutron star matter, the codes today, there's lots of sophistication in dealing with the equations of state, adding magnetic fields, etc. But very few codes go beyond ideal hydrodynamics. And this is really the equations that they solve for the bulk of neutron star matter. Okay, so now if we want to go beyond ideal hydrodynamics, if so-called dissipative effects are important, so viscosity or heat conduction, these effects become important when there are large gradients in the hydrodynamic variables, and that's sometimes referred to as sort of being out of equilibrium. And the way that that's typically modeled is, and I'll show an example later on, but for example, this is the ideal hydrodynamics equation, energy density, pressure, should mention, so this is the projection tensor, where we take the metric, the fall velocity of the fluid, so we project onto the frame of the fluid. So the way you typically handle these out of equilibrium effects are adding terms to the stress energy tensor that depend on these gradients that are now large. So for instance, gradients of the velocity or gradients of the energy density or temperature. And for each one of these terms that you add, you multiply it by a so-called transport coefficient that describes these properties. so for example, I guess the common one, the simplest version of this, at least, for example, in the Newtonian case, is the Navier-Stokes equations, where you add gradients of the velocity and the corresponding transport coefficients of the shear and the bulk viscosity. Now, it's likely that in mergers involving neutron stars that this will be important, especially for the post-merger phase, but it might even be important in the late stages of the inspiral. And that gets back to the interesting points that Alessandra made about trying to tease out the tidal deformability, especially eventually if we get very high signal to noise events, viscous effects. They're not going to be large, but they could play a role. So this is one of the ingredients that will eventually have to be added to those simulations. So how do we get a relativistic dissipative theory? Well, let's just do the same thing that we did before. We just consider velocities as full velocities, promote ordinary derivatives to covariant derivatives. And that was originally done. But one complication that's not new necessarily in the relativistic setting, but it turns out to have significant consequences, is that out of equilibrium, there's no unique way to define what you call your hydrodynamic variable. So the full velocity and the energy density, for example, that shows up in the stress energy tensor. Just to give you a concrete example, so imagine that we've got a particle flux 4 vector U sub NA. Out of equilibrium, that does not in general coincide with the flux velocity of the energy of the fluid. Perhaps the simplest scenario to think of is just imagine you're sitting in the rest frame of the fluid, so the particles aren't going anywhere, but there's a temperature gradient. So then there's going to be a flow of energy across the temperature gradient, and so there will be a non-trivial energy flux 4 vector even in the rest frame of the fluid. So I think that's a nice concrete example to think about it. So coming up with relativistic theories, using this ordinary to covariant approach was done very early on. And this issue about what's the so-called hydrodynamic frame, that's the set of choices that you make for your out of equilibrium hydrodynamic variables, that was realized early on that there was this ambiguity. And that the two choices that people made early on that sort of became the textbook example of relativistic Navier-Stokes, one was by Eckhart in 1940, and amongst other choices, so they're more than just this choice, but with respect to this example, Eckhart chose that the velocity u that appears in the stress tensor was the particle number flux full velocity. And then a few years later, Landau and Lifshitz in their textbook chose the opposite frame in this respect. Okay, so yeah, so that's fine. It's sort of, there's a certain ambiguity, and you can perhaps think of it as analogous to coordinate freedom in relativity. But the problem with this is that the Eckhart and Landau and Lifshitz theories are actually ill-posed. And actually very early on, it was realized that there was one problem with them, was that they were actually parabolic equations. And of course, if you want a relativistic theory, you don't want things to travel faster than the speed of light, but a parabolic equation doesn't respect that speed limit. So early on, it was recognized that they had a problem with causality. Though you could argue, perhaps that might just be, some unlimited cases, or there might be a little bit of leaking of energy superluminally, but it might not be such a problem. But then in the 80s, Hiscock and Lindblom actually proved that they don't admit stable equilibrium solutions, even in a simple non-relativistic setting. So for example, even something like if you used these theories to perturb, say, the ocean at standard temperature and pressure, you'd find that the oceans would blow up on microscopic timescales. So they don't admit sensible equilibrium solutions. And mathematically, it's because they're ill-posed. Now, a bit before then, but in the 60s and 70s, Mueller and Israel and Stewart figured out a way to fix the causality problem. And the way that they were able to do it was going to second order in the so-called gradient expansion. So the Navier-Stokes equations are essentially looking at first gradients and how that affects the stress tensor. By adding second derivatives of the various quantities, it becomes much more complicated to get many more transport coefficients. They were at least able to figure out how to make the equations hyperbolic. So that seemed like, sort of a very sort of a cumbersome way to fix this problem, but at least seemed to be a fix. on the other hand, it turned out that it's not such a perfect fix. And so in the 90s, Olsen and Hiscock and Garrosh and Lindblom showed that in certain situations, these so-called MIS theories cannot generically describe very strong shock waves, even in a weak sense. So in the ideal fluid case, when a shock forms, it's a discontinuity, but you can apply sort of integral methods to make sense of it. They showed that that's not possible in certain regimes of MIS theories. And so the problem with that is it's a problem of predictability. So when such a shock forms in your scenario, you're kind of dead in the water. You don't know how to resolve that going into the future. And so the Cauchy problem fails when such strong shocks form. Now, I think that quite remarkably, you think about something, this is just hydrodynamics, and it's just relativity. You don't even have to include general relativity. It's just special relativity. And so, it's only in the last few years, actually, that people really understood what the problem with the original Eckhart and Landau and Lifshitz theories were, and that actually hydrodynamics, relativistic hydrodynamics, dissipative hydrodynamics is a perfectly sensible theory if you consider this issue of frame correctly. And so what they showed was that if you up to a given order in the gradient, we'll actually just do it to first order, but at that order, what you have to do is in the stress tensor, you have to include all terms that are consistent with the symmetries of the problem. And each one of these is going to have a particular transport coefficient. Now, the microphysics of the particular fluid that you're dealing with will constrain these transport coefficients. So there is still sort of freedom there is still that ambiguity in choosing a hydrodynamic frame. So in other words, one particular fluid could have many descriptions in terms of different hydrodynamic variables. But perhaps most crucially for this example is that the choice of the frame affects the hyperbolicity of the underlying equations. And so that restricts the set of hydrodynamic frames where you can get a sensible theory of at least a sensible set of partial differential equations that you can solve. And so in hindsight, Eckhart and Landau and Lifshitz just accidentally or by simplicity chose bad frames. So they chose these frames where the equations just don't make sense. And so just to an example of that, and also that this problem that Hiscock and Olsen, Garrosh, and Lindblom identified with MIS theories about not being able to resolve arbitrarily strong shocks also arises in these so-called BDNK theories. And so BDNK, Benfica, Desconzi, Mironia, and Koftan, the people that, so there were actually several authors before this that built up to this work, but I'm sort of using their example as the sort of the first definitive answer of first-order relativistic hydrodynamics. And that problem also shows up in BDNK, but here you can explicitly see that it's also an issue of the hydrodynamic frame. And so there are a set of hydrodynamic frames that give you well-posed hyperbolic equations, but some of them have maximum characteristic speeds that are less than the speed of light. So what happens when these theories fail to resolve strong shocks is if you choose a shock wave where the upstream velocity is larger than the maximum characteristic speed of the system, then hyperbolicity fails. And so I think that, even though we didn't do this with the MIS theories, and this work with a student of mine, Alex Pandya, this is suggestive that actually even this problem in MIS theories would be resolved with an appropriate choice of frame. So just to show you exactly like what happens to first order in this gradient expansion. And this is actually with a conformal fluid. So it's a little bit simpler than the general case. So there are a few transport coefficients that drop out with the conformal fluid. And so a conformal fluid is a fluid where we demand that the stress energy tensor is trace-free. And so that gives this particular constraint on the pressure. So if you then all the remaining transport coefficients, so this Q vector is essentially sort of like a heat conduction vector. The script tau is essentially related to the shear tensor. So sigma AB is the shear tensor. And so you can see we have gradients of the energy density, gradients of the velocities. And what remains after restricting to conformal fluids are three transport coefficients. So this chi coefficient that shows up in this A variable largely, if you can think of it, it controls corrections to the energy density and pressure that arise from gradients. This lambda coefficient largely controls heat conduction, and eta is the familiar shear viscosity coefficient. So incidentally, also for a conformal fluid, there's no bulk viscosity. So all these three coefficients are present, and they generically cannot all be zero. Right? Actually, they all have to be non-zero to have a well-posed problem. Now, then the evolution equations are the divergence of this. So there's actually there's no barrier number. So you just take the divergence of the stress tensor, and that's your equation. So it's actually, so they look very complicated, but it's the same simple principle as before. So this one, let me just illustrate this one example. So this is now solving these BDN equations in a 1+1 dimensional Minkowski space setting for a strong shock wave. So again, what I mean by shock wave is you can go to the rest frame of the shock front. So you're moving along with the shock front. So it's propagating along the fluid. Here to the left, the speed of the fluid is larger than the sound speed of the flow. And so for a conformal fluid, the sound speed is 1/√3, which is 0.58. So here we chose initial conditions where the fluid is flowing at a speed of 0.87. And it's, if you will, slamming into a slowly moving fluid below the sound speed. In this case, we picked it to be 0.4. And this choice of 0.4 was just so that we are in the reference frame of the shock. So again, in the ideal case, if you did this, you'd form a discontinuity that propagates along at some speed, that's given by the Rankine-Huguenot junction conditions. Here, the asymptotic states are consistent with that. But now, as you might expect, we expect that dissipative effect is going to smooth out the discontinuity. So what we do is in initial data, we just apply some error function transition from the upstream to downstream state. We don't put in the shock profile, and then we evolve the fluid, and it should dynamically evolve to a steady state. And what this figure shows, the two panels, is exactly the same initial condition, but evolved with two different frames. Both of these are well posed, but in this top example, we chose a frame where the maximum speed is 0.85. The bottom one, we chose one with a maximum speed of 1, the speed of light. And what soon happens, so this is time here, and so the units were don't worry about the units. In the top panel, what happens is very soon after we start evolving, a numerical instability sets in, which is what the zoom in shows, and the code crashes. Whereas choosing the second frame where the maximum characteristic is the speed of light, after a while, it evolves towards a nice steady state solution for a smooth shock front. So, and then, you might say, it's, well posedness is obvious, but even in something as simple as fluid dynamics, relativistic fluid dynamics, it's taken close to 100 years for people to really understand this issue of well-posedness in relativistic Navier-Stokes. I think it's kind of remarkable that it's taken so long, but it also shows how subtle some of these issues are, and that it's not an obvious problem at all. Okay, so the second problem that I want to now address is the interior structure of black holes, and this is going to sort of illustrate this issue of gauge in numerical simulations. So the goal is here to understand what is the interior structure of a black hole that's formed from gravitational collapse, so a rotating Kerr black hole. So one thing that we even immediately know from this, the textbook example of the Penrose diagram of an eternal vacuum Kerr black hole that I've drawn on the left here, we know that that can't be physical for many reasons. So just to remind you, so in that picture, this little triangle, this is our universe, scry plus, future null infinity, scry minus, past null infinity, r plus is the event horizon, future past event horizon, r minus is the inner horizon. We have this alternative universe connected through a non-traversable wormhole. And then we have this time-like singularity when we cross the inner horizon. And I've shaded these regions blue because there are also closed time-like curves in this regime. So actually the Penrose diagram in these blue areas don't make sense. So if you want to interpret the Penrose diagram as telling you about causality in the blue regions, that's actually not, there is no Penrose diagram because it's not a globally hyperbolic space. But nevertheless, this is the structure that you get, and this repeats infinitely into the future, infinitely into the past. So it's a very interesting geometry, but it's unphysical for many reasons. And of course, the first reason for, if we think about gravitational collapse, is the past and the other universe obviously can't be there. So if we were to sort of lift this into a sort of a conception of what the interior structure might look like for a star collapsing to occur black hole. So yeah, this orange colored thing, that's to represent the material of the star. So now we have this origin at r equals 0, an asymptotically flat space-time. One can imagine that something like this is going to happen. So the star collapses through its horizon, an event horizon forms, and the question is, what's going on here? There's still going to be this Cauchy horizon. What happens sort of at the part of the question mark part of the space-time? So one thing that's even just taking hints from the vacuum picture, one thing that's very disturbing about this Cauchy horizon, this r goes to r minus part, is that curvature there for large black holes is small. If you looked at what's happening there in the geometry, you wouldn't expect quantum gravity to help you, but to make any corrections to what's going on there. But if you may imagine sort of the Einstein equations sort of from the perspective of Cauchy evolution, so we specify complete initial data on some surface sigma. We want to say, can we use the Einstein equations to tell us everything that's happening in the space-time? And if we did evolve that, if we reach something that's like this vacuum Cauchy horizon, predictability will fail. So the Einstein equations can't predict what's going on, cannot uniquely predict what's going on beyond the Cauchy horizon. And what's disturbing, if there's no singularity there, how can quantum gravity come to the rescue and tell us how to proceed beyond that? So it's kind of a pretty, from some perspective, it's a disturbing situation. Now, historically, there were several or at least a couple of main suggestions for how this might be resolved. And both of them sort of relied on the fact that the vacuum curve solution is special. Generically, they're going to be perturbations, gravitational waves from asymmetric collapse, radiation from the matter from the star, etc. And that those perturbations will cause singularities to form that will shut off the bad parts of the space-time. So one suggestion was, and this was sort of even recognized early on by Penrose and others many years ago, is if you look at sort of photons traveling along, falling into the black hole at late times, they're blue shifted as you approach the Cauchy horizon, and in fact, infinitely so in that limit. So locally, finite energy falling into the black hole is going to have infinite energy density as you approach the Cauchy horizon. And if you imagine, if you take back reaction into effect, that should cause a singularity. And that actually seemed to be consistent with studies in spherical symmetry with Rising-Nordstrom black holes and the so-called mass inflation singularity that Poisson and Israel found in the 90s. But there was another suggestion as well that would say, well, perhaps we'd never even get to a Cauchy horizon, that somewhere in the interior on a space-like surface, a strong curvature singularity more akin to what's inside Schwarzschild, or the so-called BKL-like space-like singularities in cosmological settings would form, and we wouldn't have to worry about a Cauchy horizon. So singularities would show up. Relativity would tell us that it cannot understand them, and we'd need to go with a quantum theory of gravity. On the other hand, recently, just a few years ago, de Fermos and Luke proved that if the exterior of Kerr is stable, then there must be a null branch of the Cauchy horizon that's in the space-time, and moreover, the metric can be continued in a C0 fashion across this horizon. So it suggests that there's still room for some kind of a singularity there, but at most, it's a very weak singularity. And perhaps if you want to think of a weak versus strong singularity, a strong one, like inside of Schwarzschild, is tidally crushing. It's going to destroy every object that gets there. A weak singularity, like on the Cauchy horizon, objects will survive there. They won't be tidally destroyed before they get there. And so incidentally, that they disproved this so-called C0 inextendable version of Penrose's cosmic censorship conjecture. Okay, so putting all of that together, I'd say our best guess today for the interior structure of generic black hole formed from gravitational collapse would be something like this. So the star collapses somewhere deep in the interior. There's probably a strong space-like singularity, but then there has to be this null branch, and it probably gets progressively weaker as you sort of approach the event horizon on this Penrose diagram. So these are all conjectures. So this seems like a perfect example. I mean, we won't be able to prove theorems with numerics, but if we can just give a few specific examples, that can go a long way to helping out in what's going on. But now the problem is that the only cases where numerics have been able to apply it is in spherical symmetry. And so that's severely limiting for a couple of reasons. One is, if we restrict to 4 dimensions, we can't have rotation. So we can't study curved black holes in spherical symmetry. So the proxy that people used, Brady and Smith and Rodden-Piron, in particular, was to look at charged collapse. So in Reisner-Nordstrom spacetime, there's also a Cauchy horizon. And actually, they found that this kind of picture does arise. There's a space-like branch and there's a null branch. Now it's in spherical symmetry. It's not angular momentum. It's certainly not generic. The other sort of trick that we can use to, in this case, explore actual angular momentum is to go to lower dimensions. So to look at the formation of a rotating black hole in 2+1 dimensions. And there you can form these so-called Bernados, Teitelbaum, Zanelli black holes, or BTZ black holes. But well, the downside is it's in 2+1 dimensions, but you also have to have a negative cosmological constant. So it's in asymptotically ADS spacetime. So this is an example of a simulation of black hole formation in ADS. And this is with a student, again, the same Alex Pandya with the Hydro studies. So this is a Penrose diagram, but in ADS, the infinity is a time-like boundary. That's why it's not this diamond shape. So to the left, we sort of show radius, circular radius on this diagram, and to the right is curvature variance. I'm not going to go into much detail with this, just to illustrate kind of interesting kind of structures that can form. So this is a case where it wasn't very rapidly spinning. And so here we did form a space-like branch of the singularity. Here there was actually a null branch. And actually in this region, we're not quite sure what this is, because the one thing with numerics is when a space-like singularity forms, even if things are not singular in this region, we don't know what happens to the causal future of that. And that's kind of what's happening in this region. So this could be a null singularity. It could be just the causal future of a space-like singularity that we cannot resolve. And the interesting thing here is when we ramp up the spin, the region that is space-like becomes smaller. The region that becomes null grows. The null singularity becomes weaker. And eventually, at some point, it stops being a singularity on the Cauchy horizon. And in fact, in the limit where A goes to 1, this Cauchy horizon extends all the way down to R equals 0 without any singularities. Now, that's probably a peculiarity of 2+1D ADS. So the caveat is this interesting spacetime, but because it's such an unusual situation, we cannot really say if it carries over to the GR case. Okay, so why is it such a problem going beyond spherical symmetry? And the issue is gauge. And I think it's pretty sort of evident from the Penrose diagram if you consider what would be demanded to be able to reveal the space-time starting from gravitational collapse. So imagine a Cauchy evolution. Again, we set initial data here. We want to evolve forwards. De Fermos and Luke tell us we have to be able to go all the way to the Cauchy horizon. So for this slice to evolve all the way to start seeing the Cauchy horizon, we have to evolve all of the infinity of the exterior spacetime. That's all relevant for the interior. And moreover, this part of if we run into a singularity in the interior, a space-like singularity, the code has to be robust to that. So not only does it have to be robust to complicated singularities forming the interior, it has to evolve to T equals infinity in the exterior. So that says, okay, doing it for the Cauchy evolution is just silly. We should use null coordinates, use some kind of a null evolution scheme. And the problem with doing that is when you adapt your coordinates to null curves, that typically, or generically, especially with perturbations, caustics are going to form in your slices. And these aren't geometric singularities. These are just coordinate singularities. But at the moment, and so in principle, you should be able to do something to get rid of them, but no one has proposed a way to get rid of caustics when they form. And the only case where we can handle this is in spherical symmetry, where by symmetry, we know where the caustic is. It's at r equals 0, and we can deal with it. And so in fact, like all of these simulations that people have done, they've taken advantage of the fact that we know that they've used null coordinates to some extent, and they've taken advantage of the fact that the caustic is at r equals 0. So I think it's a complete open question how to come up with some dynamical gauge or to fix this caustic problem to reveal the full interior. I should just mention that recently there was some very interesting work by Chesler et al. Where they did use null coordinates in a 3D setting, but they couldn't look at the collapse problem for this reason I just mentioned. So they just focused on a small region of the Cauchy horizon. So I got some interesting results, but again, the question is that initial data arising from collapse is a generic? Well, we just don't know. So just it's my last slide before I give conclusions. So just to jump to the other side of the other class of singularities that are often considered, and like why is gauge not a problem? And these are the so-called like the Big Bang or the Big Crunch singularity. So if you approach a singularity in a compact space-time, the reason why this is a much simpler problem is that there's no exterior to worry about. We just have the approach to the singularity. So this, for example, the Penrose diagram showing the approach to, say, a Big Bang type, Big Crunch type singularity. And for a long time, it's been known that there is a very nice choice of slicing, the so-called constant mean curvature slicing, that does approach this full singularity in a very nice way. So there's no gauge problem in this case. But then, and perhaps interestingly, so there's no gauge problem, but then pretty early on, people discovered that when you actually look at perturbations and how the singularity forms, the problem then is that you get these very non-trivial structures called spikes that form. There are very narrow features in the geometry that shrink to scale so rapidly that very quickly there's no way that the numerics can resolve it. And so then it becomes an issue of expense. We just don't have the computational resources to evolve very close to the singularity and resolve these structures. So just to demonstrate that there's a simulation with David Garfinkel of approach to one of these cosmological singularities with sort of toroidal topology. And here we had symmetry in the z direction. So we've only had non-trivial initial conditions in x and y, and they're identified. So this segment is that segment and the top is the bottom. So it's toroidally identified. What I'm showing here is a rescaled version of some scalar that you can sort of construct out of the shear components, if you will, of the curvature. So this really is diverging, but we've rescaled out the rate of divergence, so it's normalized to between -6 and 6. So I'll start this. And so now we're sort of evolving towards the singularity. And what starts to happen are these mixed master sort of chaotic transitions. And there you can see this first sort of spike that's formed. And actually at this point, we can't resolve it anymore. And kind of remarkably, the simulation doesn't crash, so we can keep going. As we go, sort of more intricate transitions happen, more complicated spike structures form, and presumably this will happen ad infinitum going to the singularity. But again, I should emphasize, when that first spike formed at around t equals 15, we lost convergence completely. The spike was completely unresolved. And usually codes crash when that happens. So here, remarkably, it doesn't crash. So this very intricate pattern that's forming, we don't know if this is really what's happening because we've lost resolution. So it seems like there's lots of interesting structure that happens here, and likely this kind of structure will also happen in the interior of, in some part of the interior of black holes from collapse, but we just don't know. Okay, so to conclude then, I think numerical methods, they're just a complementary set of tools to analytic and perturbative methods, very useful in studying gravity. And there's been a rapid evolution in the field in the past few decades. Sort of, I think, a very mature sort of sub-branch, if you want to call it that, of relativity at the moment. So there are a lot of things in which we could use it as a tool, and especially like all the work that Alessandra mentioned in her talk with binary black holes. But there's still a lot of open questions and open regimes where progress is to be made. I guess for the sake of time, I'm not going to go through the list again, so people can just sort of like read the list. Okay, so thank you very much for your time.
Many thanks to you. Thank you very much. And okay, too many singularities for me, so I give Alice space for question. I see one. Oh, sorry. One hand. I don't see him. Any? Who was with the raised hand? Please raise your hand again because I don't see you. Alessandra.
Yeah, thank you very much, Frans, for the talk. I have a question about these non-singular bouncing cosmologies. Can you tell us something about what happened recently in the topic? What has been done and what is known at the moment?
Right. So that's one of the areas where there's a lot of interesting work going on at the moment, and so this is sort of Paul Steinhardt and IHES and those then Justin Curry and those people that have sort of proposed an alternative to inflation, that to create the conditions that sort of generate the structure in the cosmic microwave background that we see today, you don't necessarily have to have inflation post Big Bang, whatever that means there, but you can have a prior contracting phase of the universe where that smoothing happens, and then there's sort of a bounce, and then the universe starts to expand and structure starts to form. So the thing that's so some of the original ideas behind how that might happen were that there was some kind of a singular bounce, so that when this happened, that classically the scale factor would go to zero, curvatures would diverge, and somehow quantum gravity would have to engineer the bounce, would have to make it happen. So the smoothing happens before quantum gravity causes this bounce to happen, and then you go into the future. I mean, that's probably a reasonable idea, but the problem is we don't have a quantum gravity theory that actually can describe that. So more recently, what sort of Paul and Anna have sort of pushed is this idea of, well, let's study this using a non-singular bounce. So let's try to come up with models where the bounce happens well away from the Planck regime, so we can trust classical theories to understand what happens going through this regime. Of course, the problem with that is that if we use simple matter models that we know, or standard G, or the singularity theorems say that we can't, they have to be singularities. And so the way that you can avoid that is either using so-called exotic matter models or modified gravity. And sometimes there's a mix between what you call modified gravity and what you call exotic matter. And so, for example, one of the common theories that are used are the so-called Hondesky theories, where you can think of them as having matter with very complicated non-standard kinetic terms, and those terms sort of evade the energy conditions that force singularities. So at the moment, there's sort of been a lot of progress in understanding that these theories in certain regimes actually are well posed, so they could be in principle applied to study nonlinear perturbations around the bounce, but that has not yet been done. So the vast amount of numerics that have been applied in these cases is in the smoothing phase prior to the bounce. So not yet putting in these Hondesky terms that could produce the bounce, but looking at how nonlinearities prior to that are smoothed. And I think the next, then there have been analytic examples of these bouncing solutions in these Hondesky theories, sort of in smooth FRW-like scenarios. So I think what's an open problem now is to sort of combine these two things. Now put in some realistic perturbations, see how they are smoothed, and now put in this Hondesky field that can actually cause a bounce to happen and see how it evolves through the bounce. So that's one of the open areas where they're, so with Paul and Anna and other collaborators, we're working towards that, but we don't quite yet have any full examples.
Okay, thank you. I don't see other raised hands. So maybe we can go for the break and leave some more space for questions at the end of the session. There's something maybe in the chat. Let me see. No, nothing. So I suggest to reconvene at 5:15 for the last talk of today. So have a good coffee.
Thank you.
I will leave open the room. So I just mute myself. Thank you.
Thank you.
Hello.
Yeah, Stefania.
Ciao.
Oh,
How are you?
I'm fine.
Oh, great. How is the situation in France?
It could be worse. It's okay.
Could be worse. Also in Italy, the same, could be worse. They want to try your slide. Oh,
yes.
Usually I show this, during the, but no one is looking at them.
Ah,
Anyway,
okay, just to know.
Anyway, take your time. We are not, you are the last. So take your time, there's no problem.
But now let me, yes. So, so this is a play slideshow.
Yes, but I don't see your screen.
Okay, so
Not
I thought I had clicked on
the green button.
On the green button. I thought I had
exactly
on it. Ah, but then not on your face, on my.
No, not on my face.
No, on my screen.
Okay.
Is it? No, because I had.
Now it's perfect. Then let me see your. Yes. Check your mouth.
Yes.
I don't see it.
You don't see?
No.
You don't see my screen?
No, I see your screen, but not the pointer.
Ah, actually, you mean this? I have not. Okay, no, the only thing I have is I did not prepare a bigger pointer. Yes, sorry.
It's up to you. If you don't need it, it's not a problem.
I have just the small thing, the small arrow.
I don't see it.
Okay, I won't. Is there a very quick way to do it?
I don't know. Alessandra,
can
you help me?
Go out from, can you go out from the full, yeah. Now, if you go on Zoom, there is options, you can open the laser, no, on Zoom.
On Zoom.
The options.
No, not on your presentation, on Zoom.
On the top of Zoom, there should be options, but if you've never done it, maybe it's not easy to.
Okay, I've done it once, but we should not lose time on this.
Okay.
I have framed things.
Okay.
Zoom disappears. Where is Zoom now?
Zoom is on the top of your screen. I don't see it, but it should be on the top, not here.
Yes. Yes. Okay. Okay, I better not to touch too much. Yes.
No, in fact, let's do like that. No problem. So.
Okay.
The screen.
Okay, so I'm.
Okay, we can start with Thibault Damour. He will speak about progress and challenges in the relativistic two-body problem. Thank you very much. You can start. Thank you.
So I start. Okay. It's an extreme pleasure to be talking at this conference. I remember very well last time I was at the Galileo Galilei Institute for the Veneziano Fest, and I had the pleasure of visiting the house of Galileo himself. So, progress and challenges in the two-body problem. Let me start. There is something going on. Do you see my full screen, or is it?
I see your full screen. Everything is fine.
Something.
And also I see your pointer. Great.
Okay.
Very good.
Let me move this out a little bit. So, yes. So I wanted to start with an allusion to a quote by Henri Poincaré, saying this is the French version, and the English version would be that there are no problems which are definitely solved, but only problems that are more or less solved. Probably he had in mind, among other things, his work on the n-body problem in classical mechanics, where this is a Poincaré section of the restricted three-body problem here on the left. But here today we will apply we will see that this sentence applies very well to the two-body problem. Oops, now, yes. I want first to make a list of the tools that have been used for attacking the two-body problem. So there are famous historical approximation methods like the post-Newtonian, the post-Minkowskian approximation method, which means expansion in gravitational constant, the multipolar post-Minkowskian or MPM approximation that we will discuss in some detail, matched asymptotic expansions, which are useful at several points, gravitational cell force, effective one-body, numerical relativity, effective field theory, quantum scattering amplitude with all its attendant tools, and the recent Tutti Frutti method. So, although there has been an excellent tutorial week, maybe some people did not attend the week or the full week, and there are also a few points that I wanted to make. So let me very briefly do a history of the two-body problem in general relativity. This was started by Einstein in actually already in 1912, but up to 1916, where he introduced the post-Minkowskian or nonlinearity expansion, and also the post-Newtonian expansion, which was particularly developed by Johannes Droste in Holland. The post-Newtonian uses, besides an expansion in G, the idea that 1/c, the inverse velocity of light, is a small parameter, both in time derivatives and also algebraically. And this led to the first computation of the first post-Newtonian approximated Lagrangian dynamics, which is the Lagrangian for two bodies with the Newtonian term, famous, and the first post-Newtonian correction, 1/c² beyond, which is usually attributed to Einstein-Infeld-Hoffmann, 1938, but which actually was derived by Droste and Lorentz already in 1917, but then forgotten for a long time. Now, higher post-Newtonian approximations were tackled at the end of the 60s and in the early 70s by Chandrasekhar and Nutku, Chandrasekhar Esposito, for radiation reaction by Burke, Thorne, conservative dynamics by Ota, Okamura et al. But although there were many useful results in these works, they also uncovered infrared difficulties. They realized that using the post-Newtonian approximation and the fact that this was only a near zone approximation, which was more or less understood at the time, created infrared divergent integrals. And also, actually, there were no correct results at the second post-Newtonian approximation, nor fully at the 2.5 PN approximation. The root of these infrared difficulties was that physically, when you solve Einstein equations, you want to impose retarded wave conditions, which means that although you solve Einstein equations, here it's a toy model where if you solve a scalar Klein-Gordon equation, massless Klein-Gordon equation, D'Alembert equation in Minkowski space, the general solution will be an infinite sum of multipolar waves, derivatives of scalar retarded waves. And when you expand them in 1/c, what is a wave which decays at infinity grows in the near zone. So the idea of matched asymptotic expansion was used by Burke to deal with this, but as we had shown later with Luc, actually the technical implementation of this idea by Burke and Thorne was flawed, although the final result was okay. And this led to the return of the post-Minkowskian approximation method, especially after the discovery by Hulse and Taylor in September 1974 of the binary pulsar, which was quickly recognized as an observational handle on gravitational radiation reaction in the system that should change the orbital period. And actually, in December 1978 in Munich, Joe Taylor announced that the orbital period of the binary pulsar PSR 1913 plus 16 decreases modulo, within 30% plus or minus 25% of the quadrupole formula heuristic derived orbital period change of the binary pulsar. But this then led many physicists, notably around Jürgen Ehlers, to say that the existing derivations of radiation reaction and more generally the dynamics of binary system in GR was not satisfactory. First, as I just said, because there were divergences appearing in the expansion due to this near zone, wave zone incorrect matching, and also because there were actually no derivation of the 2pn dynamics, which is even before the level of radiation reaction. So this motivated a certain number of physicists, starting with Arnold Rosenblum, Westphal, and then a group in France, to use a post-Minkowskian approximation method. The basic idea was to say, if the problem is to have retarded interaction between two word lines, then you should use consistently a retarded propagator and never separate the near zone and the wave zone, but just compute nonlinear interactions at, let's say, one loop. So this is the one graviton exchange. This is a nonlinear effect due to gravity, and this is, as a diagram, one loop, and this is two loop, and you needed to go this. So this was done in around the early 1980 by this group in France, so using this retarded propagator. But then, in order to make contact, after getting the post-Minkowski invariant equations of motion, they were expanded in powers of V over C to be able to discuss explicitly what aspect of the dynamics is conservative and what aspect is radiation reaction. And it was found explicitly that the 2.5 PN equations of motion had an expansion of this type. The up to 1 over C4, it was shown that they could be derived from Lagrangian, which was acceleration dependent in harmonic coordinates. And this is the full form of the equations of motion. And there was an extra term at 1 over C5, which was dissipative. And then it was shown that its effect on binary system exactly explained what was observed in the binary pulsar. Okay. To do this, there were several challenging issues, subtleties that are still with us. And I want, as the main idea here is to point out challenges which are still open. This is the idea that you are talking about the motion of neutron stars, and neutron stars have a strong internal self-gravity, and therefore you cannot use actually weak field theory everywhere to deal with that. And you have, for this, to separate various space-time regions and distinguish the strong field region, the weak field region, and then match them by using matched asymptotic expansion. And then you have to prove that seen from the outside, you can represent the extended objects by point masses. And this introduces UV divergences when you replace, extended bodies by point mass in a nonlinear theory. And this led to the discussion first of the Love number of compact bodies, neutron stars, to the proof that the Love number of black holes was by definition essentially, because of the Noether theorem, 0, and to the proof that you could still use the word line in a nonlinear theories by using an analytic regularization or a dimensional regularization, okay? This is still a challenge today because it was later shown by Cole and Smolkin that the fact that the Love number of black hole is 0 is true in 4 dimensions, but not in other dimensions. So there is the question, when you use dimensional regularization, should you still consider that there is a vanishing Love number, which with some UV divergences might contribute? Recently, a 5PN computation by Blumlein et al. Has shown that there is no need for this, but this is something still, in my opinion, to be clarified. And then we will discuss later the issue of infrared divergence appearing at 4 p.m. So after this early effort based mainly on the post-Minkowskian derivation of radiation reaction at 2.5 p.m., the idea that soon LIGO and Virgo should detect gravitational waves led many scientists to develop better methods for gravitational wave generation, how to compute to high accuracy the gravitational waves emitted by binary systems or general matter sources, and also how to improve the equations of motion of two-body systems. And this led us, I mean, Luc Blanchet, Bala Ayer, and myself, to develop the multipolar post-Minkowskian method that I will explain briefly. And this led Jaranowski, Schaefer, Blanchet, Fay, and others to push post-Newtonian calculation beyond the 2.5 pn level. First, let me discuss quickly the perturbative theory of the generation of gravitational waves. This is something which dates back to Einstein's early quadrupole formula work in 1916, 1918. This was extended in the 50s, 60s, 70s. And then with Luc Blanchet and Bala Ayer, we developed, using ideas of Bonner, Rothenberg, Epstein, Wagoner, Will, Thorne, we combined several approximation methods to have a way of dealing with nonlinear effects in the wave zone. So the basic idea of the multipolar post-Minkowskian formalism is to decompose space-time in various overlapping regions, like a near zone, which is this thing, NZ, near zone cylinder. This is a space-time diagram around the material source. Here, let's say a binary system. Then an exterior zone, not a wave zone, but an exterior zone, which includes part of the near zone, but then goes up to the wave zone. And then you need technically also a far wave zone where there is a bonded type expansion. But basically what you do is in the exterior region, you solve Einstein equation by a post-Minkowskian expansion, a nonlinear expansion, but at each order, you solve the wave equation that appears, including inhomogeneous nonlinear terms, by using retarded Green's function and expanding the solution in multipolar expansions, okay? And then this defines a multiple expanded nonlinear exterior solution, and then you need to match it to the solution post-Newtonian expanded now near the source, okay? And what this is important for is that it allows to explicitly compute radiative multiple moments, that is to say the wave zone, the waveform at infinity decomposed in multiple moments in terms of the source distribution. And but many nonlinear effects appear on the way, like this Uij is a radiative multiple moment encoding the waveform at infinity when you expand it in spherical harmonics, and it is expressed, in terms of other multiple moments, algorithmic multiple moments M, which are themselves expressed in the source multiple moments, which are expressed as integrals over the source. But the source here is not only the stress energy tensor of the source, but also evidently the nonlinear energy density in the near zone, which appear here. But also you need to add tail effects, memory effect, and tail of tails, etc. I will come back to this. This led, thanks to this work and mainly of the group of Luc Blanchet, to the computation, for instance, of the quadrupole moment of a binary system, currently to the 3.5 pn approximation, explicitly given by these formulas for circular orbits. And currently there is a challenge of extending this at the 4 pn level. There are preliminary results by Marchand et al., which are incomplete because they are subtleties linked to UV and infrared divergences that appear at 4pm. And this is one of the challenges for the future to compute this. From this, you can compute the waveform expanded in multiples or the gravitational wave flux and get explicit formulas. Alessandra has explained and Alessandro last week during the tutorials how this was used. One of the main points I want to emphasize here is that this work with Luc Blanchet allowed to understand in 1988 an interesting effect which now plays a very important role, which is that there is a breakdown of the post-Newtonian expansion and the idea of separating a near zone and a wave zone at the 4pm level, because you have hereditary effects which are transported via tails, but then reflected back on the curvature of space-time, and they strike back on the system, but at time intervals which are as large as you want. So it's not something that you can expand in a short time delay in powers of 1/c, because this is really non-local in time given by this type of integral, and this has been incorporated in 2014 explicitly in the 4pm action. At this point, I want also to share some concerns I have about challenges concerning asymptotic space-time structure. After the work of Bondi Sachs, Penrose found a very elegant reformulation using conformal transformation at infinity, scribe plus and scribe minus of the Bondi type expansion. And this led Penrose to define asymptotically flat spacetime at null infinity by this definition taken from another paper of Ashteka. But essentially, this says that there exists a conformal transformation such that you can smoothly transform the metric at infinity, okay? But this definition actually is implies the peeling so-called theorem, which says that the curvature scalars at infinity should scale from the curvature scalar which measures radiation in 1/r down to the one that measures as far as you are from radiation, that should scale down as you go far away from the system, like 1/5. But actually, it has been shown by several arguments, calculations, and theorems that one should not expect this peeling theorem to be correct. There are violations of peeling shown by these authors at scribe minus, even in linearized theory. And in 1986, I had shown that if you consider precisely a scattering problem with massive body coming in at minus infinity and scattering, even if they don't scatter, even if they merge actually, on scribe plus, the psi0 Newman-Penrose scalar does not scale like 1/r5, but this scale only like 1/r5, 1/r4. And also the general results of Christodoulou and Kleinerman on stability of Minkowski spacetime point out strongly to the fact that the generic solution of Einstein equation should violate peeling. And also, I must say that in spite of the nice tutorials on BMS and soft gravitons last week, I still fail to understand in what sense the BMS group is a symmetry, because I tend to think that actually the only global classical symmetry, when you take into account the link with the source and the global structure of spacetime, will be the Poincaré group, and that the BMS is an ambiguity if you know only partial information about the connection with the source, but I don't see it as a symmetry. Now, but this is an important topic for further discussion. Now, another challenge and topic for discussion, which is now quite important technically, is how can one separate the dynamics in conservative and radiation reaction effects? I already said that in principle, if you can use really post-Minkowskian approach with retarded propagators, you can expand it later and then see what is conservative, what is radiation reacted. Within the Hamiltonian Arnovitt-Deser-Misner approach, this is done in a different way by solving constraints in a Coulomb-like gauge and then integrating out the radiative degrees of freedom in the near zone. Another approach is to use the Fokker-Wheeler-Feynman approach, which says that the only way to define a conservative dynamics is actually to use a time-symmetric Green's function. And then this defines a conservative dynamics. And then the force you need to add to ensure balance with fluxes at infinity, you call the radiation reaction force. Actually, this is the way it was used in the EOB approach, where one used balance, modulo short terms, between mechanical energy and angular momentum and gravitational wave fluxes to include radiation reaction forces in the EOB approach. Recently, in the EFT approach of Goldberger-Rothstein, there is a distinction between potential gravitons and soft gravitons, which allows to separate partly radiative effects and conservative effects. And I will discuss later the tutti frutti approach that we have developed recently. Let me just to clarify the Fokker. So Fokker in 1929 was the first one to explicitly show how, starting from, let's say, the Maxwell field interaction between charged particles, you can integrate out the Maxwell field. If you use a time-symmetric Green's function, this would be a one-photon exchange diagram. And then this gives this explicit two-word line interaction, which actually played an important role in Feynman discovery of Feynman diagrams, but I don't want to discuss this now. In the gravity case, you can do the same thing, except that you are in a nonlinear theory. So you need to integrate out using the time-symmetric Green's function. This was done in work with Esposito Fares, how to do that. The one graviton exchange, then you have this effective action written here explicitly, you know, for two word lines at one loop and then at two loop, etc. But one of the challenges of these things is, which is still, I think, a bit unclear in the literature, is physically, you would like to use the retarded Green's function written here in the X space or in momentum space. If you define the conservative dynamics with the symmetric Green's function, which in P space is like that, you need to add radiation reaction. If you use a post-Newtonian expansion in the near zone or potential gravitons, actually you use a PN expanded near zone thing, and the Feynman Green's function actually is different from all of these. And then you have to discuss whether you are talking about in, out, Schwinger-Keldysh, etc. Now, I want to, although there have been excellent tutorials last week by Alessandro, and Alessandra has given a beautiful review of how the effective one body is constructed and used for waveform models. I want to just mention a few historic points. The effective one body approach was historically rooted in a work of Brezin-Itzikson, Zin-Justin, about resummation of econal scattering amplitude. And it was also based on the idea that it's very convenient when you want to map a classical, the two-body problem on an effective one-body problem, to think quantum mechanically by using Bohr-Sommerfeld quantization. But let me redefine in one word the effective one-body dynamics. The effective one-body approach says that the conservative dynamics of a two-body system should be equivalent to a mass shell constraint for one particle moving not only in an external metric, effective metric G mu nu effective, but also with Finsler type higher non-linear, non-quadratic in momenta extra terms. So you have a mass shell condition, which is p square plus mu square, the reduced mass, plus some extra term. And also, crucially, you need an energy map between the effective energy of the two-body, of the one-body problem, and the real energy of the two-body problem. I just want also to show something which is striking. This is the explicit post-Newtonian expanded 3pn level Hamiltonian, which is quite complex with many terms. And when you transform it in EOB dynamics, it is equivalent to something remarkably simple, which is this mass shell condition with an effective metric which is spherically symmetric and therefore described by two functions A and B. And the function A is written here in terms of GM over RC square. B, or the product AB inverse, is represented here in this function D bar. And there is an extra quartic in momenta term that you need to add. But it is remarkable that you have condensed a very complicated, I mean, all the information of the 3pn Hamiltonian in just, 1, 2, 3, 4, 5, 6 coefficients. I also want to say that for historical amusement, that so the effective one-body idea and the idea that you could define up to merger the dynamics and then make a matching at the merger and have a complete waveform was compared by Buonanno, Cook, Pretorious to the first simulation of Frans. So this work was published in 2017, and in their work they showed what was the numerical relativity frequency of the gravitational wave during merger. Merger is here, so this is the end of the inspiral, this is merger, and this is the ring down after merger. And this was the EOB prediction at the time using 3pn dynamics, the one I have just shown, and using absolutely no numerical relativity information. I just want to emphasize that here, without using any calibration to numerical relativity, the agreement was already significantly satisfactory. And later, soon with Alessandro and Luciano Rezzolla, we, by calibrating only the dynamics, we could, and using EOB without other calibration, show that indeed the EOB was describing most of what numerical relativity could give, and that finally, from the 3pn effective Hamiltonian given by this function A, like what replaces 1 minus 2m over r, the numerical relativity calibration was quantitatively relatively small information that you needed to add, although it's an absolutely crucial one in order to describe very accurately the merger. I want now to mention that the effective one-body framework is a convenient framework, not only to define templates, but also as a focal point where you can inject information and combine information from various approximation schemes like numerical relativity, self-force, multipolar post-Minkowskian, post-Newtonian, post-Minkowskian, but also scattering amplitudes in quantum field theory, string theory, and effective field theory. And there is currently a very useful dialogue going on. Let me mention some of the recent progress done in collaboration with Donato Bini and Andrea Giralico, that we call the tutti frutti method, because it mixes a variety of methods, post-Newtonian, post-Minkowskian, they are all Delaunay averaging. And this method allows, modulo the fact that there are two unknown coefficients appearing at 5pn, to determine completely the 5pn dynamics, okay, which is the state of the art. So by using other information, one could use this. And this diagram also shows that at any pn order, this method, the tutti frutti method, allows to compute all the black dots, okay? This is a representation of the Hamiltonian decomposed in powers of momenta and powers of gm over c square r, so powers of the gravity of, if you want, g. So this is the post-Minkowskian order, and this is the post-Newtonian order. And at 6pn, for instance, you are here, and only the white dots are unknown at some pn orders. At the same time, this method shows that if you go too far in pn, there are many white dots, so it becomes less useful. I also want to mention, because during the tutorials, it was maybe not clearly said how non-local effects can be included in UB. So I said before that starting at G4 and at the 4pn approximation, there are non-local in time interaction. I mean, due to very soft gravitons that are emitted by the system far away in the past, that are scattered on the curvature of space-time and backscattered on the system much later in time. So this leads to conservative, non-linear, non-local interactions due to these soft gravitons. And at 4pn, for instance, this is described, here it is at 5pn actually, this is described by this non-local Hamiltonian, non-local action, where this time split gravitational wave flux. And what I just wanted to say is this is not an obstacle to using the EUB Hamiltonian description, because you can use the so-called Delaunay method, standard method in celestial mechanics, to use expansion for small eccentricity of this thing and then represent this in EUB framework. Now let's go to the scattering issue. And first, the use of gravitational scattering as a tool to understand the gravitational interaction. First, I want to mention that this was an idea in the PN expanded framework, at least, which was started by Corinal Dacey in 1956, and then Barker, Gupta, Arras, and many people until recently. But this was in a PN expanded point of view. I want to say also that this can be done by comparing to numerical relativity simulations, by using also self-force computation. I won't have the time to discuss this, but Leo Barak is giving a talk later in the week. Post-Minkowskian, both classical and quantum, okay? First, let me mention briefly that in 1914, it was possible to do numerical simulation of scattering, and including scattering. Now, you know, it's not small angle scattering, because here you see the scattering angle is nearly 180 degrees. The two particles come along these lines, this line, and then, sorry, it's more than, it's like 360 degrees or whatever. I mean, they come here, they do one turn around each other, and then they go at a completely different angle. And then we could compare the result of numerical simulations, except that at the time we had the problem that numerical simulations evidently are radiation reacted, because you emit gravitational radiation reaction. So we took the result with Donato Bini to correct for radiation reaction in the scattering angle. And this led to a very good agreement between numerical relativity and EUB. I want to mention that, and Frans mentioned this, but nobody took up seriously this challenge recently, that it would be interesting to have ultra-relativistic scattering of black holes to be able to compare to radiation-reacted effective one body, and to learn something about the dynamics. Now, concerning the post-Minkowskian perturbation theory for classical gravitational scattering, this was started by Louis Bell and Schuss Martin in the 70s, and then Westphal, and then I have taken up the story recently by showing how to write up a dictionary between a scattering angle, the scattering angle that you can compute. Here it is the impulse, and here, by the way, in two lines, you can compute the one graviton exchange impulse, and then in one line more, you can transform it in EUB language. And what I had shown is that if you expand the classical scattering angle in a power series in Newton's constant, or the inverse impact parameter, or inverse angular momentum, each term in the expansion can be transformed by simple formulas. So the first term is this one, the second term is this one, and then there is a very simple way of transcribing this scattering angle as a function of energy and angular momentum in the EUB Hamiltonian. Each term in this term Q here can be simply written as a linear combination of the expansion coefficient of the scattering angle, okay? So that one could get, for instance, very easily what is the 2 p.m. Exact dynamics to all powers in V over C. And then at the time, there was the only existing calculation at higher order, at order G cube, or 2 loops, was done by Amati, Ciafaloni, Veneziano. And then there was the issue of can you use the information in this econal scattering angle of ACV to transcribe it in EOB language? And I did that. I showed how to use formally the ACV result to have the G cube, so 3 p.m. EOB Hamiltonian. And at the time in my paper, I urged amplitude experts to use their novel techniques to compute 2-loop scattering for massive particles in order to deduce the 3 p.m. Hamiltonian. And this was done by the group of Zwibern. And the surprise was that when they computed the 3 p.m. scattering angle, it had a logarithmic divergence at high energy, which did not agree with the logarithmically finite Amati, Ciafaloni, Veneziano result. And this was a puzzle for a while, especially because at the beginning, I thought there was some like technical error or conceptual subtlety there. But finally, several people checked that this was correct at 5 p.m., at 6 p.m. So clearly the result of Zwibern and company was correct. And then this was clarified thanks to initially a work of Paolo Di Vecchia, Heisenberg, Russo, and Gabriele Veneziano, and then me, resurrecting the idea. I mean, their main idea was that the radiation reaction effects, which were known, I mean, for a long time, to start scattering in the scattering angle at the G cube over C5 level, but which had always been viewed in a post-Newtonian expanded way as a small correction, actually, they play a crucial role when you take their high energy limit. So the idea is when you discuss conservative dynamics a la Fokker, Wheeler, Feynman, you are considering that you have the two bodies in space-time, but they interact by time-symmetric graviton interaction, which means physically that there are waves coming in from the past and then that are then re-emitted in the future so that the system conserves energy. But if you have a scattering where waves are emitted only in the future, then actually this will create radiation reaction forces that will change the scattering angle. In general relativity, so a calculation had been done in supergravity by Paolo Di Vecchia and collaborators, and showed strongly that this should happen also in GR. I was able to do the G cube calculation in GR by I must say, surprisingly simple calculation in the sense that it's finally just a few lines to do the computation, how to compute the radiation reaction contribution at order G cube, treated as a correction to the conservative scattering angle, which is G plus G squared plus G cube. And using a previous formula, using a result which dates back from our youth with Nathalie Deruel, and using other results, especially by DeWitt on the angular momentum loss at infinity, a simple calculation gives the contribution, radiation contribution to the scattering angle. And lo and behold, when you add this, it cancels exactly the log divergence of the result of Zwibern and gave the Amati, Ciafaloni, Veneziano finite result at high energy. But now, so at G cube, the situation is clear. Now, beyond G cube, there are new challenges, and several people are certainly working on this, including ourselves. Recently, the group of Zwibern has succeeded in computing the potential graviton contribution to conservative G4 dynamics. So it is only part of the answer, which needs to be completed by several types of radiation-related contribution. First, there are conservative radiation graviton non-local contributions, which are important. These are already included in the Tutti Frutti framework. So we have computed these in detail to complete the result of Viburn's. But there are also other radiation reaction contributions that we have also computed. We are preparing a paper on this. Several papers are relevant in this venture, like the work of Fofa and Sturani on NLO radiation graviton contribution to the EFT dynamics, recent work by Johannes Blumlein and collaborator, work by Herman Parra-Martinez, and our work. Let me just mention one result which comes out of this. We were able to compute using this the two currently unknown, missing, if you want, 5pn parameters at the new square order of the EOB dynamics, so of the full 5pn dynamics, A6 and D bar 5, which are given by these pi square contributions, which have already been obtained by Blumlein et al., although they do not give any detail on exactly how they got the radiative contributions. And we could explicitly compute the rational numbers in terms of other quantities. And results on this will be discussed in an upcoming paper. As the main idea of this talk is to mention challenges, I want to finish about emphasizing the various challenges in the translation between quantum scattering amplitudes and classical dynamical information. Because at the beginning, it seemed that people from the amplitude community said, okay, there is no problem, everything is clear, we know how to get classical dynamics from quantum amplitudes, but maybe there are still, I think there are subtleties in this. I mean, the main subtlety that I want to emphasize again is this fact that Niels Bohr emphasized many times, that the domain of validity of the Born Feynman expansion, the quantum expansion, is opposite to the domain of validity of classical scattering, because roughly speaking, okay, the domain of validity of the Born expansion is when the analog of the fine structure constant, let's say alpha G, which is G times the energy of the two scattering particles, divided by H bar, is smaller than 1, because you are doing an expansion in powers of this dimensionless constant. So you want this to be small. But the domain of the classical scattering is H bar going to 0, which means that alpha G is very large. Another way to say this is that when you are in the domain of validity of the Feynman expansion, actually the wave packets, you cannot make sharp wave packets which are well separated. They must overlap, okay? So how do you deal with this? Partial ways of dealing with this, which had been emphasized by many people, starting with Damour, Bierum-Born, others, is to focus on non-analytic terms, also Cachazo-Guevara, I should say, in Q, okay, this has been explained in the tutorials. Then there is a problem which has been tackled very clearly by ACV, which is actually you want to prove that you have an econal resummation. But to me, it is not totally clear. I mean, I understand the idea of econal. I know that there are partial results about econal, but can one really prove that which part of, in presence of superclassical terms, which part of the amplitude really will exponentiate and which part will be a quantum correction? It's not clear to me. There is a nice framework by Kosover, maybe O'Connell, to compute the quasi-classical impulse. And this has been used recently by Parra-Martinez and colleagues. But the problem I see with this is that this calculation has to assume that you have a good approximation methods for the amplitude. But if you are in the regime where alpha is much larger than 1, are you sure you control things? And also, although I don't want to sound negative, to me, the recent results seem quite complicated. Finally, as we will show in our paper, one can get the G-cube radiation reacted impulse by very simple classical means. And the quantum calculation now looks more complicated than the classical one. Anyway, to end up, I will just show again this nice thing of Henri Poincaré, which is that the two-body problem is still is only more or less solved, and this leaves many challenges for the future. Thank you for your attention.
Thank you very much for this excursus, both historical, very complete, but also with a lot of still open problems and a lot of work going on. So we expect results in the near future, because you are a lot of many collaborations on that subject. So it's very exciting. Okay, I see one question. Luke, you can unmute yourself. Okay.
Hello, Thibault.
Hello, Luc.
Thanks for the talk. I have a question or a remark regarding what you said in the first slides of your talk about the derivation of the radiation reaction by Burke and Thorne at the lowest order, 2.5 pn, 1/c5. I am not sure that actually the derivation was flawed in the sense that the result is correct, and in the gauge that they are using, the radiation reaction comes only from the linear contribution which they have computed. So they start from the metric at some linear order in harmonic coordinates, and in harmonic coordinates we know that the radiation reaction has many nonlinear terms that have to be taken into account in harmonic coordinates, but they perform a linear gauge transformation, and in that, after this linear gauge transformation, the radiation reaction is just coming from linear effect. They don't prove that in this gauge there are no nonlinear effects, but actually this is true, and their derivation can be extended very easily at nonlinear order, and they could have proved, they didn't, but this is correct, that there are no nonlinear corrections to the radiation reaction at linear order. So in the sense that they forgot the nonlinear terms, but they are zero actually.
Okay, thank you for the comment. Yeah, it's not flawed. By the way, something similar happened with the old Corinal-Deci computation, where he claimed to derive the Einstein-Infeld-Hofmann dynamics from a one graviton exchange. And there is the issue, is there a gauge where this is true? I think that in this case, it was really flawed, that until anyway, you have proven that nonlinear effects that are the same order do not contribute in the same way. This is an incomplete derivation.
Absolutely, yes. I have another question, but maybe later, as the chairwoman wants.
Actually, I don't see other questions, so you can go ahead with the other.
It's a remark about what you said on the BMS group. So let me make a statement, and I'd like to know if this is in agreement with what you have in mind concerning the BMS group. Generally, in physics, symmetry is very important because when it is symmetry at the level of the Lagrangian, because of the Noether theorem, then we have physically meaningful invariance associated with that symmetry. However, the BMS group is not symmetry at the level of Lagrangian, but it is symmetry at the level of some metrics. There is a class of metrics, Bondi type metrics, that are invariant under the BMS symmetry. So in that sense, this is not a fundamental symmetry group, and I wonder if you would agree with this statement, and this is what you had in mind, more or less.
I think the situation is even more complicated or subtle than this, in the sense that I think that Abe, Ashtekar, and Ströbel have shown that okay, it is a symmetry of the phase space of the symplectic form and phase space dynamics on Scribe plus. So and therefore you can derive Noether quantities. My main point actually is it's not enough, to be connected with a structure which is only on Scribe plus. If you are not rooted in the matter, okay, if you are not globally rooted in the matter that create the space-time, then this is maybe a symmetry of a partial part of the action. But I'm not sure about what I'm saying, but this is what I have in mind. That, by the way, I wanted to understand better what Monica Pate said about the QH and QS, whether, okay, and the link, okay. I did not follow all the works of Strominger and others on this, so I want this to be a topic of discussion also, because maybe it's a symmetry at the quantum level with soft gravitons, maybe not at the classical level. I don't think it is fully clear.
Okay.
Okay, Gabriele, you can
unmute myself.
Okay.
Well, I have a couple of questions. One is about the failure of this peeling theorem in psi-0. Does it have consequences? Because I mean, usually when you do this Bondi-Sachs analysis, you don't go as far as 1/r⁵. So I wonder if, what is the physical implication of this violation of the peeling theorem?
Yes, you are fully right. As usual, this is a very good physical question. I did not have the time to discuss. Indeed, it shows that there is a violation of the Bondi expansion at a high level. Now, it is not totally, I think it comes in at the level that both interest us, where angular momentum is defined, So when we are talking about linear momentum loss and all that, peeling will be okay, the waveform is okay. But this is, let's say, an open problem for me. Okay, I think it is not clear. Maybe your paper in preparation, and I am also thinking about this. I think there is something to clarify there, okay? What I know is in our old work, for instance, we knew that there were divergences in the angular momentum, except if you were linked to the center of mass of the system, real divergences. In some of the work, for instance, of Luc and Marchand and Guillaume Fay, on the K, on the boost conserved quantity and associated flux, okay? They were also finding divergences if you are not in the center of mass things. So, okay, I think there are, and I think that the usual arguments saying, okay, we have this Scribe plus and thing, and indeed this is the 1/r⁵, so it will not mess up things. Okay, it's not clear.
And then, okay, then I have a question about your paper in preparation. Are you saying that you now have the full, say, scattering angle, including radiation reaction at 4 p.m.?
No, we are saying that we are computing all the PN expand. We are computing what we can and trying to clarify several things. But it will be, okay. What we are saying is that we can rederive the full G³ impulse, okay? Not only the scattering angle, but the impulse G³ in a simple way. At G4, we have only PN expanded information of various pieces that I hope will be useful for helping future PM calculation. Nothing PM at G4.
And then if I may, since we have time and no more hands, your discussion about BMS with Luc, I don't know if my understanding is correct because I'm pretty naive about these things, but my understanding was that these super translations are a way to connect different vacua of a theory. you know, at these large gauge transformations, you know, which don't vanish at infinity. So my very rough understanding is that these super translations connect different vacuum. There is a vacuum degeneracy, and this is why, you know, this is typical of the Goldstone theorem, right? When you have vacuum degeneracy, then you have a Goldstone mode, spontaneous breaking of a symmetry. So I wonder if this sounds, you know, like what you or Luke.
Yeah, no, this is a very good formulation. What I had in mind was more, you know, saying, let's say at this rough level, that given an in vacuum, fully defined, no incoming radiation,
yeah,
that classically there is only an out vacuum and there is no degeneracy. If only you look at the out region and you are not connected to the in region, indeed you don't know which Minkowski space up there is the good one. Okay, you have this ambiguity, but I think that when you are rooted and you have the in-out transition, I mean classical transition, then you don't have an ambiguity of the out state. That's all what I'm saying.
Yeah,
compatible. It's compatible with what you are saying, but
yeah,
you're saying the out as the degeneracy, but I'm saying if you know the in, the classical dynamics determines the out, including all the soft modes. I'm saying something trivial. Okay.
Yeah, yeah. Okay, I think this will be an excellent subject for the following weeks, you know, to have a big discussion about this. Looks very, very interesting. Thank you, Thibault.
I see Luke again with the...
Oh yes, thank you very much. There was the question by Gabriele on the peeling. Let me add that, let me consider gravitational waves generated by a real astrophysical source. For instance, if we take a binary system of ordinary stars, the emission of gravitational waves is completely negligible until there is a non-gravitational mechanism or effect which brings the two black holes very close to each other, and then the gravitational waves starts to be generated, emitted. In that situation, gravitational waves are emitted only at some finite instant. And in that situation, in that case, one can prove rigorously that the peeling theorem is satisfied under this hypothesis. So I would say that for astrophysical sources of gravitational waves, the peeling theorem is true.
Yes, but look, yes, I should have mentioned this. This is fully correct, but as you remember, we had to assume that the source, everything was stationary in the infinite past. The calculation of 1986 I am mentioning is when you have a scattering situation, which means the in state is made of two or more massive particles coming from infinity, and this is a time-dependent initial state. And this is what messes up the Scribe plus, okay? The peeling.
Exactly, I agree. I exclude this case. I consider just a binary system, which is born.
I fully agree. If the binary system,
okay.
But I understood discussing with Ashtekar, there is a concept of strong asymptotic stationarity and a weaker one. And it is not clear to me whether the case of the collision of two particles or black holes, you know, belongs to this, doesn't belong probably to this strong stationarity.
No, it does not, yes.
But I think it's stationary enough. I mean, you have a mathematical criterion, which I don't remember now exactly, to determine whether.
Yes.
In some cases, for instance, apparently the definition of angular momentum is unambiguous. In the other case, it can have a BMS ambiguity. But okay, again, a subject.
Yes, and I think my point is in the scattering situation, actually, this is where you have ambiguity. Both
you have full ambiguity. Yeah, that's right.
And
so, yeah, okay. So, I agree.
Okay, I think also that there'll be a lot of time for discussion, these issues in the following workshop time. Just a comment by Riccardo Sturani that he wrote in the chat. I will talk about choice of green functions, boundary conditions in my talk on Friday. So we have also this opportunity. And I think we can close this session. Let me remind you that we would like to have your slides. Please send them to the organizers or to the GGI Secretariat, and we will publish on the webpage. People are asking for your slides. And also that this all this conference is live streamed. So today we had also more 40 participants for the streaming. And that's all for today. I really want to thank the speakers and all the participants for this very nice and useful discussion, and see you tomorrow at 3.
Thank you also from the organizing committee. Thank you, speakers.
Thanks a lot. Have a nice evening. Bye to everyone.
Bye.
Tomorrow.
Bye.
Ciao a tutti.
Bye.